Hey everyone, how are we doing? Happy Saturday morning, Claire, Jackie, Liam. Good to see you here. Leo, Cassandra, and Kaya. Great to see you here, everyone. We need Mubot to help us out. We're starting today by going over the formula sheet. Mubot can tell us about review 3. My hair is all crazy today, but what's new by you? Claire, great to see you there. We'll turn on a little music here. Ashton, good to see you. Nick, good to see you. We need a little wake up music. We need something more energizing on this Saturday morning. On a Sunday morning. It's not Sunday yet. Hey, Carter, good to see you here. Nick and Ashton. A little energizing music. Got our coffee. Good coffee. Okay. We are going over to the formula sheet. Did the Kahoot already happen? It's tomorrow. The Kahoot is going to be tomorrow. What's good, Patty? Good to see you here. The Kahoot is tomorrow. Let's over to the main screen. And let's talk about... Oh, I need a note. Did I close down the notepad? Oh, did I close down my notepad? What time? Probably around... We're going to review. And let's try to set the Kahoot right towards, like... What time is the review extravaganza? Like noon? I think it's at noon. So let's do the Kahoot at 2. So let's do the Kahoot at 2. We're doing like in sections. I figure this is easier, and we're bookmarking all the videos. So let's aim for 2 p.m. Kahoot. I'll send more announcements about that. Good to see you, JT and Tessa. Okay. Throw out some Mubot points. Okay. Tons of people. I love it. Tons of points. Tons of people here. Okay. Got everything ready to go. Let's head over to the main screen. Let's do this. Okay, so if you're looking for where I'm at right now, look no further than the chat. So there is a 12 again, then a Kahoot. Yep, that is the plan right there. I think we're doing noon tomorrow and then 2 p.m. Kahoot. So that's the plan. So if you're looking for reviews, there's the reviews. And let me take the timestamp of where we're at. Where to find review material. So I do want to point out that this is the review material here. It's got the playlist, review tests for the videos, speedrun videos, chapter reviews. This is an excellent playlist. These are videos I made in winter 2019. Still remember going to the studio to make them. I think I say, yep. But if you go through these, you can walk through a test right here. And these are excellent, excellent videos where Brian walks through a test from start to finish, talking about the 1 proportion z test, the notation on it, doing the example when we solve it, solving for the z, solving for the chi-squared or the z, solving for the p-value, and then rejecting or failing to reject the null at the end of the question. So you get a really good step-by-step procedure of what we are doing and how to solve the equations. So I highly suggest checking this out right here. This playlist is one of my favorite ones. It's got a step-by-step for all the different tests, the conditions, the 4 steps we do, and just the test, the chi-squared, the 2 sample t, the t-test, and the proportion. Doesn't cover confidence intervals. We did that yesterday, but check out this playlist if you're on leisure. There are other playlists right here that also contain things like tools and techniques, chi-squared, all the material right here for you to go over. Great stuff. Now, this covers exam 2/exam 3. It's just when I made this video, the material was on exam 2, but it does denote where exam 3 material starts with the idea of confidence intervals. These are test questions here, so you can see broken apart. And I go through and solve the practice test questions where you can see, I'll turn down the audio. So you can see a solve of each practice test question. And you get the question, and then you get the working through, and I show the math on the screen and everything we would do to solve it. So check it out. I would say work the practice test and then work these, and then take a look at the video to solve with it. So it's going to show you how to solve it and explain the answers. I make a lot less jokes in these videos, so they're a lot less fun. But if you want some videos where you just go straight through the material, where you just focus in on for 5-10 minutes and probably have a sheet of paper out working beside you or taking notes, these are the videos to do it. These are the more serious videos where you're not kind of getting interaction like we do here when we're live. These are standalone videos where you're going to see me solving through equations, talking about how to do things like test 2 means right here, talking through the mathematics, the equations, the notation. With that said, it's time for the formula sheet, which is found right here. Okay, let's download the formula sheet. Well, we might just need to take a picture of it. We're going to talk about the formula sheet now, and we're going to do every portion of it. We're going to do example problems with it and go through the formula sheet. But how's everyone doing? Where everyone got so quiet as I got serious right there. It's like, no. How's everyone doing? Let's see how the chat's doing as I get this set up right here. Chat gets quiet and I'm like, where'd everyone go? So formula sheet. One sample proportion. Good to see. Yeah, Claire. Awesome. Thank you, Claire. Take a timestamp on this. Tired as you. Same here, Leo. I don't know. I've been sleeping like 6 hours every night and I need to sleep more. Okay, let's get started right here. Here we are. Nervous. You got this, Carter. Send that good energy right there. That's awesome, Tessa. Take a little break right here and we can start the formula sheet and try first weekend without assignments. So we're going to do a little studying right here. And notice how we have proportions right here. Now, as soon as you see proportions, what should you be thinking when you think proportions? When you see proportions, what are you going to be thinking? If you see proportions, you're going to be thinking, okay, I have what right here? The tools and techniques are cumulative. Well, the z-test, that is correct. We are doing a z-test. What kind of variable are you working with? What kind of variable are you working with? If you see proportions, what kind of variable are you working with? That should be something we should categorical, right? Great job there, Leo. A categorical variable. So as soon as you see proportions, you're thinking categorical. And this is always the y variable of interest is what we're talking about. The y variable, excuse me. The y variable of interest is what we're talking about right here. And that's the one we want to understand. Good to see you, Ben. And so let's take a look at these equations and think how they apply. For the time being, so we don't look at too much, I'm just going to screenshot only what we're looking at here and go to a new Word document so we can focus. Okay. You bought limits random after I saw you were live. I'm wondering. Pretty soon, Peyton. That's the grader's catching up. And so pretty soon should be released. We've got the projects pretty graded and ready to go. And then we should be releasing the finals. We're not going to show the answers till the final period is over. So you'll have to wait a little bit on the proctorial finals. So that way people who have taken it can't share answers. But pretty soon here. Good questions, Peyton. So with this right here, we need to know the notation to begin with. Let's start each of these by talking about the notation. Now, take a moment right here on this screen and see if you can tell me. You're welcome, Peyton. Take a moment and tell me if you can tell me any of the notation. What am I talking about? I'm talking about these things. Can you tell me any of these things right here? Which of these do you know? Let's see how many we have, actually. Let's highlight how many we have. We have 1, 2, 3, 4, 5, 6. I think that's it. And I guess this is technically 7. P hat. What is P hat? What is P hat? We need to know all the notation. P hat. What is P hat? When would we use it? It is the first thing I highlighted. That is correct. So what is P hat? What does it mean? When would we use P hat? When would we have a P hat? P hat is equal to, P hat is the sample proportion. The sample proportion. So questions that have P hat in it would say something like 55% of our sample were from Tennessee. The important thing to note right here is it's from a sample. So this will do a little like yellow right here, I guess. Sure. This is an example. We'll do an example with each one here. Who can tell me another one? See how many of these you can do without me, and then you'll understand how to read them in questions, and maybe come back, like try redoing this video right here to see if you could then mark all of these and tell me what they are. Standard error. So we have a standard error. I'm going to do one next real quick right here, because if we have p hat, then what's a really easy one to find, and great job there, Leo, finding even more. If we have p hat, then what's a really easy to find if we have p hat? Anytime we say p hat, we usually just find q hat like that. Great job there, Leo. So if we have p hat, we have q hat, and q hat is the complement. So complement of the sample proportion. So in this example here, what is q hat? Now this is something we just practice quick and we get it down in my example problems here. If we know p hat is 55% or 0.55, so this as a decimal, 0.55. So we can do it as a decimal or a percent. Proportions can be changed to percents accordingly. Either which way. Rock knows.
It doesn't matter.
Rock, you gotta calm down, my man. He's so happy about that. And 45%. Great job right there. Good to hear, Patrick. So 45% is correct. There we go. And so if we take this right here, we can get q hat, which is just the complement, which is 45% or as a decimal 0.45. And Leo is correct that SEP hat is the standard error. So let's go ahead and take this right here. Now, what is the standard error? That one's a little bit weirder to interpret. We don't really interpret it that much, but the standard error is a metric of variation in the variable. So you can see it right here in notation that SEP hat is equal to p hat times q hat over n square root. You are given these equations, and it is used in the confidence interval. So you would take, I think we can go right here. Well, I'll write it out. This equation right here would be written as p hat plus or minus z star, more on that probably next, times p hat q hat over n square root. Notice how this is right here, the standard error. So this is the standard error right there. That is the standard error. So is that the standard samples? It's standard errors come from a sample. Good questions there, Tess, 100 points. Standard errors come from a sample where the standard deviation comes from the truth. You'll see the difference down here that the standard deviation of p hat uses the assumed truth p naught q naught over n. It's minor differences in wording, but so we don't really test you on it. So don't worry too much about interpreting what a standard error is. It comes from a sample. It's an estimate of the variation created from a sample. So like theoretically, don't have to know this one too much, but it's basically estimate of variation obtained, estimate of variation in proportion obtained from sample, where the standard deviation of p hat is, the standard deviation of p hat is estimate of variation obtained from the truth, or the population, the truth, assumed truth. If you notice the differences in the formula, are that when we do SDP hat, trying to show them both on screen at the same time, SDP hat right here uses P naught Q naught, and those are assumed truths, where standard error P hat uses P hat Q hat, which are the sample. So that brings us to P naught Q naught. So P naught Q naught are the what? What are P naught Q naught? So who knows these? A lot of times people forget these because this is where we get into testing now. Good to see you, Roman and Ashton. Now we're into testing. So who can help us out with P naught Q naught? So take a moment, see if you know P naught Q naught. We're talking about this portion of the equation right here. P naught Q naught, because P hat minus P naught. That's the sample proportion minus the what right here. P hat minus P naught. So what is P naught? P naught goes with H naught. So what is H naught? That's the null hypothesis. So if this is the null hypothesis, not quite the true proportion. P, which we don't see on here, P is actually true proportion. Good work there, Ashton. Good try at it. True proportion. As in UT, of all UT students, 52% are from in-state. So this goes with the population size. We got an example right here of when it's used. These are more just solved in equations. It's the null proportion. So null proportion or hypothesized. So null or hypothesized proportion. We estimate or hypothesize. We could put a hypothesize. we hypothesize that 50% of students are from in-state. So this is a hypothesized or estimated or tested. It's the one we are going to use in our equations to see if it's true. We're going to start off believing when we have a null proportion. So you can see it down here. I'll use it in an equation. If we have a null proportion, we're going to use it in the null hypothesis. The null hypothesis for the testing here would state H naught, which is the null hypothesis says, the true proportion is equal to the hypothesized. So using my example question, how would you plug it in here? And we'll say it's not equal to. What would the null hypothesis be right here? The null hypothesis would be what? And then try reading as a sentence using the words we've created right here. So if you plug in my value of P naught, then what would the null hypothesis be here? We'll see what people say. The null hypothesis would be what? So use the value of P naught that I have and then plug it in so we could write out like a null hypothesis. Well, that is correctly 100 points right there. That is correct. And then write the full thing out. I guess you don't have to write the H naught, but the null hypothesis would be P naught equals 0.50. And the alternative is P naught not equal to 50. And so when you think about this, what are you saying? You're saying the null hypothesis states that the true proportion, that's P, is equal to 50%. Remember, we're saying that that is P naught. The proportion of students that are in state is, and the true, that is pretty good right there, Tessa. Tessa, 100 points. I'd probably say the true proportion, or it's actually true that 50% of students are in state, and the alternative is that it's not that 50% of students are in state, the true proportion. We do like to throw true proportion in there because we're saying for the actual proportion, like this is the actuality, or the population proportion, which is true. I had a teacher who would say true population proportion. It's kind of redundant at that point because truth is for the alternate. Truth is for the truth is for the population. Like if it's true that 50% of students are in state, then that's what the population is. So it's redundant, but it doesn't hurt to hammer down our point a little bit more by saying true population proportion. Thank you, Dr. Seaver. The true proportion of students that are in state is not exactly. Great work right there, Tessa. More points. You're getting it. That's excellent. So we can see how these are used right here when we say the true proportion is equal to the hypothesized. Notice how this right here is the hypothesized in our examples. So we're just plugging in P naught. That is the value of P naught. It's what we're hypothesizing is true. So that always goes in that third spot in notation for writing nulls and alternatives, the hypothesized value. It'll work that way when we get to other examples here shortly, but those are the values. I guess we don't have in here Q naught. Q naught's nice and easy though, because, and we don't really use, we'll use it in the equations, but the complement of, so it's just the complement, it's 1 minus. If P naught, the true proportion. Yeah, exactly. Great job with their test. That's a great format. Excellent work and good practice. The true proportion of whatever we're talking about is equal to, because it's the null, and then whatever the hypothesized value is. Third blank is the, yeah, Tessa. That's worth 1,000 points, Tessa. Be reading the chat. Tessa's got some great notes in there for doing the null hypothesis for proportions. Great work, Tessa. If we hypothesize that 30% of UT students are in state, what is Q naught? Nice and easy questions. If we hypothesize 30%, so that's P naught, what is Q naught? This is where we have to know how to do complements just like this. If P naught is 30%, what is Q naught? These are the ones that after you do them 20 times, you're like, come on, Brian, it's easy. There you go. Priya, great work, Priya. It's 0.7 or 70%. So these can also be expressed. And we can just hypothesize anything. We can hypothesize anything. So if we hypothesize 30%, then the Q naught. So for the true proportion of blank is great. Yeah, Tessa, excellent work. Yep, because the alternative can have different signs. And this is the true proportion. Just want to make sure people know that you can express these as decimals. Probably a lot of people do because they're proportions. What is Q in this example? Now, we don't know the truth when we're doing these tests or confidence rolls. So we wouldn't notice Q isn't used up there. What is Q in these examples? What is Q in these examples? Like using this right here, what would Q be? I need to change this number. So nice and quick, nice and simple. Boom, right there, pre another 100 points, 48, because they're just complements of each other. Once you've done that a bunch of times, it's as quick as it gets on solving those. The last thing I think we have for the notation for all this, and I'll try to leave the screen here in a second, is we have N, which is the sample size. Please tell me if I miss one, like if I'm oh, we have Z too. N, which is sample size. It's lowercase n, sample size. We spoke to 200 students. So that would be our sample size. Ooh, X. Let's go over that here in a second. Now, let me see. 1,000 points on the line. Can you tell me what X is? This is a little bit more difficult a question. We're going to talk about what X is. This is equal to number of successes in the sample. So can you tell me from my work right here, I'm going to give it a second, but you really understand what X is if you can find X from the fake problem we've written out here, the fake information we've given. So the fake information we've given for all this stuff right here that we've written out, if you can find what X was throughout all this, you really know it. 1,000 points on the liner here. See if you got it. And then see. So remember X. So here's a good check right here, Leo. X has to be a whole number. X is number of successes. So it's kind of like a count of successes. So it has to be a whole number. So if you're thinking about what is X, Priya, very close. You're on the right track, Priya. You're using P though. Tessa, 1,000 points, Tessa is correct. So Tessa, what could you do to check that? Because let's say right here, there were 110 students from in-state. So what can we do with this information? There were 110 students from in-state to find out, just theoretically here, that we've created a problem that could be done. Who knows how we could use this information? So Tessa's probably going to show us, or who's going to show us how 110 is the right amount of successes to keep this information coherent on the screen. What could we do? X over N, correct. We use X over N to find P hat right here. So go ahead and show me in this example. 110 over 200 equals 0.55. And take a look right here. We have P hat right here, which is this, 0.55. And then we have X is 110 right here. So we kind of mathed it out. And then we have 200, which is the sample size we use for this problem right here. So you can tell that 110 of the students were in-state out of the 200 total we spoke to. So we spoke to 200 students and 110 were in-state. So kind of understanding how these numbers are used and the examples we have right here. Last but not least, we have Z, and the Z has a star on it. The star is actually super important. So actually we have two Z's then. So this is Z score used, or say critical value, used to create confidence interval. We'd say use a Z-score of 1.96 to create a 95% confidence interval. Now the other Z-score is used for testing the different standardized. Sure. Find the Z-score of this problem. We're gonna find if the sample proportion was unusual given the null proportion. We're gonna do problems with these in a second, but there are a lot more than I would write out right here. So that would be creating a conf roll and find if this is unusual. Now, I think a point of confusion that we often have right here is that people see the Z-score right here. Let me highlight this. They see these two Z-scores, and they think, yes, they're both Z-scores. This is ZP hat. I don't usually mark it that way, but that is just the Z-score of the standardized difference. The top of the equation right here is just a difference between two numbers. You're subtracting two numbers, and then we take and we standardize it. So every test you're going to see right here is going to be a difference up top, standardized, where a confidence interval has a different format. A confidence interval, is going to have an estimate, and then plus or minus a what? What is this portion over here called? Everything after the estimate, after the plus or minus rather, is called a what? Everything after the plus or minus is called the what? Good to see you, John. Everything after the plus or minus is called the what? The what? The margin of error, correct. So a confidence interval serves a different purpose. Great job, Rona. It's going to be the margin of error. Shanice, good to see you too. So we have a margin of error, and we get a interval to estimate what the truth is, or we could test a value. So confidence interval estimates the truth, and a test tests a value. So they can do similar things, and a confidence interval could be used to test values, but they are a little bit separate right here. They do kind of separate things, but they can overlap in what they do. But do realize, once again, what I do want to point out is that are these z-scores the exact same thing right here? Are those z-scores right here, these ones, this one right here and this one down here, the first and the second one, are those z-scores the exact same thing? Like this z-score right here and that z-score down there, are they the same thing, yes or no? No, they're not. This z-score up here is when we say make a 95% confidence interval and use a z-score of this, make a 90%. Why does it have the star? Because the star is based on the percent confidence. There's a theoretical problem. There's a theoretical possibility they could be the same, but we often don't. Yep, I'll show it here in a second, Tessa. And then down here at the bottom, this is when we test a value and we find out how far it is away from our sample, and then we standardize that difference and get a z-score. And from this, we will then find a p-value. Confidence intervals don't find p-values. They estimate what the truth is and give you an interval. And then the bottom here gives you a probability of your result. Let's go ahead and zoom out right here. I'll try to make it so we can see everything on one screen, nice and neat. I think that's, here we go. Tell me, anybody, if you want me to move it. Tessa, is that good right there? I'll have it like this. This is everything we wrote down. It's a lot. That's a lot of stuff right there. That's all the notation. You're welcome, Tessa. Anytime, yeah, feel free to ask. If you're watching anyone, feel free to ask while I'm doing stuff, because that way, because we'll keep going, and just be like, hey, can you do this? And we will do it. We'll run out of coffee is what we'll do. Okay. So now let's actually use, let's make the confidence interval. Let's run the test. We're going to use the values from previous. Please tell me if I forget the values. We went out and spoke to 200 UT students, and 110 of them were in state. Make a 95% confidence interval using a z-score of 1.96 given to you on the test to estimate the true proportion. Okay. Then interpret the interval. Okay, who can do this right here? Take a moment, see what you get. I have a guesstimate of what it'll be. I've done a lot of ones with this it's probably going to be about 51 to 59%. That's my guess. Who's got this right here? 1,000 points on the line. People are saying, I need those points. If you can solve this, let's start marking our notation. It's the same notation from the previous set of work we just did. Let's see right here. Mebot talking away. We've got right here this. We got right here this. Mark your notation. So I'm marking the notation as we do this. We got here n. We got here x. X over n equals p hat. So p hat is equal to 110 over 200. That is 55% or 0.55, whichever way we wish to express it. Probably working with decimals, I would suggest, especially while doing the mathematics, to keep it in decimal format. That's how the equations work. And then once we get p hat, we can find q hat. So that's p hat, so 0.45 equals q hat, same numbers we were working with before. And now we need to put it through the confidence interval format. This is the z-score right here. And so there we go. Oh, I was a little bit off. Priya, great work right there. I said 1,000 points, right? Priya, excellent work. That seems to be correct. Let's see. And then make sure everything, I would say do not round till we shouldn't take off if you enter more decimals than needed. But so do what the test says and tell us if you see any errors. But it never hurts to enter in more decimals in my view. Never hurts to enter in more, because I can't imagine emailing an instructor and being like, hi, I entered more, like, don't just do it randomly. But if you're like, should I enter in more? I would suggest entering in more. If you are concerned. If the problem says enter to 3 decimals and you're pretty sure you've done it, but the problem might tell you to report as a percent or as a decimal. So make sure you do it the following ways it asks. Read each problem carefully and please contact your instructors if you feel like the problem didn't count you correctly. I've corrected many tests. We don't make perfect tests, we make great tests. Okay, so we need to plug in the numbers right here. Oh, great. Priya's given all. Yeah, I would have given the extra I would have done 48.1 Priya to 61.9. 61.9. I would have done that right there as the decimal points right there. Okay. I was thinking there was another decimal. We are just plugging in the numbers right here as we do this. And it doesn't same answers we are because it's just easy to make calculator errors. You'll see me make them all the time. So just try plugging it in, see if you get the same answers. It's like practicing using the calculator. Good practice. That's the standard error right there. So that portion is the standard error. We're then going to times this by 1.96. I always rewrite this now as the margin of error, 0.0689. So that is the margin of error. And there it is. And I'm going to trust Priya right there. It does look like Priya has it correct. A lower bound of 0.481 and upper bound of 0.619. Great job, Priya. Do you know when we will get our projects back? Monday at the latest. They lot got them back yesterday, and then Monday at the latest is they have a deadline by then. So that is their deadline. We're 95% confident the true proportion of UT students that live in state is contained in the interval blank to blank. Priya, another 100 points. That is correct. So when we do the confidential interpretation, we always say, I am blank percent confident that the true, then here's the hard part, blank is contained in the interval blank to blank. And so this is the confidence interval right here. I am blank percent confident that the true blank is contained in the interval blank to blank. And Priya said it perfectly right there. We are 95% confident. You can say we or I, that's either fine, that the true proportion of UT students that live in state is between the interval. That's fine too. And then just give the interval. There you go. Great job. The interval goes right here, lower to upper. And so now we're on to the other problem we have, which is going to be testing the proportion. Now, I did something crazy right here. I hypothesized 30%. Now, can anyone tell if I hypothesize 30% and I see 55%? Now, this is not how we do statistics. You got to watch out. We don't do statistics just by looking at things. But if you do enough stats, you can start to look at them. Like, well, you just contradicted yourself. Well, do stats for 12 years, and then you'll be like, oh, you can look at that and tell. So when you look at it, we believe that only 30% of students are in state. What have I given you right now? What value have I given you by saying we believe that only 30% of students are in states? We want to see if this is true or not true. We go out and speak to 200 UT students. Great job, Leo. You are correct. 100 points right there. That is the null proportion. And find out, or let's change this. Find out 55% are in state. This time we didn't give X, we just gave the percentage. Perform a 4-step hypothesis test to test your belief. Okay. So what is the first step to doing a hypothesis test? What is the very first step to doing a hypothesis test? If we have a hypothesis test, we need a what? Good to see your tie. If we have a hypothesis test, we need a what? If we have a hypothesis test, we need a what? We got to write those hypotheses. So we need to write out our null hypothesis, which states the true proportion is equal to what we hypothesize is true. We hypothesize, great job, Zach, right there, and we put the equal sign. So we write out our null that I believe that the truth is 30%. This right here is P naught. And P naught goes right here, the hypothesized value. This is the true value, and we always say that the truth is equal to what we hypothesize. And then you have to look to the question, not the data, the question, not the data. And the only thing that changes between these is the sign. So remember, look to the question, not the data. I can't say that enough. We do have questions that say that. Look to the question itself, like what we're trying to investigate. We want to see if it's true or not, like if it really is. And then, so the alternative here is the not equal sign. And the only thing that changes between these two is the sign. The null has the equal sign. And then the alternative, based on the question, not the data, chooses the sign. So now that we've done step 1 right here, of writing our null and alternative, and which one of these is believed at current time till we have evidence otherwise? Step 1, write null and alternative. Which one of these do we currently believe right now? We believe the null. Great job right there, Leo. So currently believed. And need evidence to believe. So we would need evidence to reject the null and say we have evidence for the alternative. So the alternative is the evidence-based claim. The null is the current belief. We're like saying, I think 30% is true. Say, why do you believe that? I don't know. I just think it is. You don't need reasons. You just say, I think it is. Pretty right there solving the problem. It's pretty far away, right? So now the next step is to find the z or the t or the chi-squared. Now, z goes with proportions. Find test statistic. Z or t or chi-squared in our class. Here we'll do chi-squared that way. No. Oh my. There we go. Okay. So to find the z, the t, or the chi-squared, that's what you saw on the previous screen. So we need to take right here. I'm losing my mind. And with this, we're going to plug into the equation z equals to p hat minus p naught over p naught q naught over n. Now, we use p naught and q naught down here because they're assumed to be true. You might say, why not p hat, q hat? Well, those are estimates of the truth. So if we think p naught, we right here, p naught is equal to p, then aren't we actually just using p and q? I mean, we're not, but right now we believe that that's the truth. So if we believe p naught is equal to p, which this says up here that this is p right here, well, then we would have this. I think when I realized, I was like, oh, since we assume it's true, we use it. So that's used as the assumed truth down there in the equation to figure out the variation within it. And then if it's the assumed truth, it's just a standard deviation, not a standard error. That's a little bit of theory. If you know the equation and what to plug in, you're good. But that's the theory behind it. So over here, we need to then put in the numbers. Priya has solved it out. Thank you so much, Priya. Another 100 points. Where is it? Oh, p hat is 0.55. There's the difference up top. Remember, try to solve this with me. See if you get the same numbers. Okay. And the standard deviation. That's square root. There it is right there. And then the difference. There you go. To solve it. So the answer is 7.7, which Priya said right there. The standard deviation was this on the bottom. Solve your work right there for the bottom. And then the difference up top is 0.25. Think 55 cents minus 30 cents, 25 cents. So if you take 25 cents, that's the difference up top. I have no idea what's going on. There we go. And then divided by that, you get the following, 7.71. Now, the next thing we can do theoretically, we don't really have test questions. I hate it when it does this, when it says like, you shall not pass. There we go. It's like weird sometimes. Cool. Step 3 right here is to find the what now. What is step 3 to our test? Now that we found the z-score of 7.71, or 7.72, we'll round it. Now that we found our z-score, what is step 3? We have our z-score. Now we need to go and find our what. We have our z-score. We need to go and find our what now. If you have a z-score from a test, the z-score is then used to find the what. The z-score is then used to find the what. Now that we have our z-score, we find our what. Find the p-value. So we're going to find the p-value. Now, this not the best one to do on the test right here, but this one can be theoretically solved for. The p-value is basically this. So who knows what the p-value is basically for 1,000 points? Who knows what the p-value is basically? Basically this. You can kind of theoretically solve it, because if you draw it, which I always suggest people draw and then make an estimate of, I need to make my curve more sloped like that. I need to draw better normal curves. After 12 years, I need to draw even better normal curves. Basically zero. Great job right there. Basically zero. And so what do we mean by that? So take a look right here. We landed at a z-score of this right here. So we have to go 7 standard deviations above. So 4, 5, 6, 7. We're all the way. We're further off than I wanted to draw, than I could get to. We're all the way over here, which means we'd also draft down here. And so the area is off the curve. It's so far off the curve that there's like nothing. Does that point? Oh, we can actually figure it out, Leo, really quickly over here. We can go to p-norm. I think it should be this one, right? Nope. Yep, that's, wait. There it is right here. Times by 2. Options. SciPen 20. There it is right there. There's the p-value. Close, Leo. That's the p-value. So we have ways of finding it out, especially with statistical software, to figure out the proportion, or not the p-norm. I never remember p-norm, q-norm. I always get them reversed. You don't need to know those, the integration of the curve, but you can find them out. It's basically nothing. Imagine if someone gave you that much of a pie, and you'd be like, you gave me nothing. We care more when it's closer in. Like, I want you to think about this for a second, just so you can see what's happening with these and how they're found. What if I told you, like, what if we solved this equation and we obtained a value of 1 for the z-score? This is just a hypothetical for a moment. Now, remember, we're doing the does not equals test. Can anyone estimate the p-value for me now on the does not equals test, which is going to take our results and then plot a result just as extreme? We're just doing a hypothetical right here. Can anyone tell me, because we would go to our result of 1, that's the z-score of 1 we landed at, and then we would go to a z-score just as extreme on the other side and shade the other side of it. So what would the p-value be now, hypothetically, if we had a z-score of 1? So use your knowledge of how the curve works to say, if we had a z-score of 1, it should be about this. Great job right there, about 32%, right? And you can see this if I go over to my software and just change this to 1. I'm going to make it so it's going to look a little bit nicer. We're going to go to SciPen of this, and then we're going to take this and round this to 3 digits. And there, oh, wait, what'd I do? I lied. Oh, that's the z-score. Oh, I might enter in the wrong thing. What am I doing? My brain broke, everybody. Oh. We don't want... I know what it is. There we go. There's 32%. If you really want to see 32%, there we go. 32%. So 1 exactly. Reason being, and don't worry about the statistical software. I'm just using it to show. It does the area below it, so I was actually doing too much. What I'm doing right now on statistical software is I'm finding this area right here and then doubling it on the other side. When I entered in 1, it found this area right here and then times it by 2, which was too much. So you want to find the area left of it, and you want to find this area and then double it on the other side. So I was supposed to enter a negative. My brain was like, wait, what went wrong? So it is 32% basically. And if you're looking for the ways we do it in our class, we use the visualizations from the David M. Lane. Now, once again, you're just meant to understand things at this point, like z-scores. I don't think we don't really have many, just like maybe like rejecting the null hypothesis, things like that. So we can go to what our problem actually says. we wouldn't expect you to find z-scores like this. The p-value here is basically 0. So we know that, does that make sense right now, Priya? Like if you had access to an applet, you would go over here and enter in the z-score outside of negative 7.72 and 7.72, and you get a p-value of 0. This is visually what it looks like right here. So the p-value is about 0, which brings us to our next step, which is a lot more test relevant. Probably spent too much time on that portion, but let's go to the next step right here, which is way more test relevant, which is to do what? Now that we know the p-value is 0, what would you do right here? We found the p-value. It's 0. So what would you do right now? Now that you have the p-value, reject or fail to reject the null. And this is what we were doing yesterday. We were rejecting or failing to reject the null. And with this right here, the p-value is 0. So when the p-value is low, when... Oh, do we still have this from yesterday? We still have our sheet from yesterday, I think, where we wrote everything out. I'm going to find that. Here it is right here. This is from yesterday, so check out yesterday's work where we went over and did this. There it is right here. And here's the steps you need to do. We would need to know our alpha level. Remember, we just found the p-value of 0. Good stuff from yesterday. Yeah. P-value equals 0. Alpha equals 0.01. So try writing this sentence right here. We are using a p-value, or p-value is 0. Alpha is 0.01. So try writing this sentence. This is good practice for the test. Make sure you can write it out when talking about rejecting or failing to reject the null. So remember, when the p-value is low, you reject the null. You'll make one of two choices right here. Here's your first choice. Here's your second choice. And that'll lead to the first or the second choice down here. If you say, I do not reject the null, or I reject the null, you would say, I do have evidence. I can't even keep them straight. So what do we have right here? Our p-value is low, right? When the p-value is low, reject the null. When the p-value is high, just let it fly. Don't reject the null. So I would say, I reject the null hypothesis that the true proportion of UT students that are in state is equal to 30%. We wrote that out way earlier. That's what we wrote right here. The null hypothesis that the true proportion of UT students is equal to 30%. This is on the exam. We practice it. This is on the exam. We talk about how to interpret and read our results, and then it does say it. And then this is exam prep right here. So we're doing, like, does that make sense, Zach? Like, we've done interpretations of it. Step 4, which is interpret our results, the 4th step. But this is where, like, I'm like giving you like a structure to be like, this is how I would do it. I reject the null hypothesis that the true proportion of UC students that are in state is 30% at the alpha level of 0.01. Check the problem right there, with a p-value of 0.0000. This means I do have evidence for my alternative that the true proportion is not 50%. Wait, so if the p-value is greater than alpha, we fail to reject the null. If the p-value is below alpha, we reject the null. Correct, Tessa. When the p-value is low, reject the null. When the p-value is high, just let it fly. And what do we mean by low? That's right, Tessa, right there. We mean lower than alpha. When the p-value is lower than alpha. So when the p-value is low, reject the null. And what is low? Smaller than alpha. So the way we know this right here to reject the null is the p-value of 0 is lower than the alpha of 0.01. Alpha is assumed to be 0.05. This is alpha right here. I reject the null hypothesis that the true proportion of UT students who are in state is 0.3. Does that make sense right there, Priya? I reject the null hypothesis that the true proportion of UT students that are in state is 30% at the alpha level of 0.01 with a p-value of 0. This means I do not have evidence for my alternative that the true proportion of UT students that are in states... No, it means I do. Sorry, I do have evidence for my alternative, because I do right there. I reject the null hypothesis true proportion is 30% in the mixture of in-state students or something. Leo, give the context. Good stuff right there. That's probably, I think, all the points right there. Excellent work. This is some of the tougher stuff, some of the tougher interpretations. No worries, no worries. That's really great right there. Probably, I might give all the points. Yeah, we want it to be as good as possible to make sure you're communicating the ideas and understanding how to do it. And this was a really good example right here. Like, I'm hoping, yep, of course. We've got the p-value thing down here. I could remove. I'm trying to bring it up so it looks all pretty. What? Okay. There, let me leave the screen. There it is right there. Write the null and alternative. Find the z, the t, the chi-squared. We could also check conditions right there. Random, 10%, and success failure, at least 10 successes, at least 10 failures. There was 110 successes and 90 failures. So there we go right there. Oh, excuse me. We had to do expected successes, P naught, NP naught, and Q naught. So there was 60 expected successes, 140 expected failures. So the condition would technically be NP naught and Q naught to check for expected successes, expected failures. NP naught and Q naught. And our P naught is 30%. So that would be equal to 200 times 30%. And that is equal to 60. And if that's equal to 60, then that's equal to 140. There, right there. How likely is it that the conditions will not be met? Very unlikely. We usually meet the conditions. It might ask you to check conditions. So it might ask you to check conditions. We would want to say these are randomly selected students, less than 10% of all UT students. And then the NP naught and Q naught is known as the success failure condition. We usually meet the conditions. I can't say they all will, but it's more likely than not conditions will be met. I can say that. So more likely than not, your conditions will be met when doing test questions. Only if needed. Yeah, the question will direct you, or there'll be theory questions about conditions like which of the following was not used in the problem? So which of the following conditions was not used in the problem? Multi-select. There's no multi-select. No multi-select on the test. Okay. Which of the following was not used in the problem? Not questions can be weird. So that problem we just did right there, random, 10%, nearly normal, expected cell count, independent means. Which numbers were not used in the problem? So this is just a trivia one right here. There's no question on the exam. I'd say it looks quite like this, but see if you could answer this question right here. Which of the following conditions was not used in the problem? 4 was not used. Expected cell count is chi-squared. So we'll do it in red because I don't know if that's showing not used. So chi-squared. That's correct. 4 was not used. When is 4 used? 4 is used for t distributions, or t, which is quantitative. And then what else do you notice? What else do you notice? Oh, and then Leo got the other one. Leo got the other one too. Leo was right. Independent means right here, because that's also t. Because if you see t, it's if you see means, it's quantitative. So those are the ones not used right there. Does that make sense? Not really a good, there's no test question that looks like this, but this is a good way of understanding, okay, wait, we did random, 10%, and success failure. Nearly normal is for quantitative distributions. Independent means is when you have 2 means, which is quantitative. Expected cell count is chi-squared. I guess I could have put in another one right here, which is almost all of them, I think. I could have put in count data, and that's also chi-squared right here. And we'll go over those more here in a little bit, but the count data would also be chi-squared, which was not used. Is there something like a chart that shows every condition that is associated with every test? I did write one out. If anyone has, I'll try to find that here in a little bit, but I do have one written out where I do the steps. Those are all, I think so, right? These are all the conditions, correct. And so you have everything right here, categorical. So here we'll highlight right here the different groupings. So this is a quick sheet of it right here. When would you use independent means? When would you use independent means? When would you use independent means? When you have 2 means and you want to see if they're independent. And I think, Priya, we now have all of them, and we've color-coded them by the test they are used for. So there is all of that, all the conditions right here. Random and 10% are always the first ones we talk about. They sometimes are different order, but I always like to do them first because they're for everything. So you have to have randomly collected data, less than 10% of the population. Nearly normal is the shape of the quantitative distribution, needs to be nearly normal. Expected cell count, at least 5 expected cell counts in the chi-square test of independence. When we're doing the chi-square test of independence, working with 2 categorical variables, which is count data, success failure is at least 10, expected success is at least 10 expected failures, and independent means is for the 2 sample t-test. So we could put 2 sample t right there. When you have the 2 sample t, you have to have the 2 means are independent right there. So that's the 2 sample t, but this also applies to 1 and 2 sample. So that's the 1 and 2 sample t. Does that make sense? Like a 1 sample t, 10% means that we sample less than 10% of the population. Why or why not do we pass the 10% condition here? Can you explain to me just in words real briefly, why do we pass the 10% condition here or not? Yep, yeah, well, that's what we're doing right here. That's what we're doing, Zachary. We're about to do the next section of it. We just finished basically a whole lecture on proportions right here. It's a categorical X. I think you're talking about that, Leo. It's a categorical X, quantitative Y. The conditions are always based on the Y variable. So the Y variable being quantitative means we are analyzing a Y variable. We're splitting it apart, but the Y variable is still quantitative. But no, Leo, that's great questions because isn't there a categorical variable involved? But the Y variable of interest, the one we're interested in describing and understanding, is quantitative. 200 is less than 10% of the UT population. The 200 students we sampled is less than 10% of all the UT population. Because there's like 30,000 students. So you could do the mathematics right here where you said something like 200 over. And we might, like if we said the population of the US or something, John, great work, John. 200 students is less than, I'd probably go with less than. Can you go back down? Of course. Thank you everyone for being here and asking these questions. Here is the full sheet right here. Disappear, and then we're going to do the next part of the formula sheet, Zachary. So stay tuned. We're about to do the 1 sample t-test next. And these are in-depth reviews right here going over pretty much everything. And what does expected cell count mean? We have at least 5 expected cell counts for the chi-square test of independence. And so we'll be doing that condition here in a little bit, Tessa, where we have at least 5 expected cell counts. The conditions right are over here. And there they are. So expected cell count is at least 5 expected cell counts. Can you just open the same stream in another window and pause it? Yeah. Leo, great. Wow, Leo's got some pro tips right there. You could open it on another account too so we can get more viewers. I'm just kidding. Oh no, Leo, great pro tips right there, Leo. Some people have told me they put the stream on their TV and then they take notes on their computer and they watch it on their big screen TV. I think that's so cool. Like first student who sent me, they're like, I have you on my TV. And I was like, that's cool. That's cool. Okay. So be taking these notes. That's what matters. If you're here and you're asking the questions, you get priority on what we talk about. We are going to get through the formula sheet though. That's the goals for today, is to go in-depth review of the formula sheet. So we're on to the next portion of the formula sheet here. We're going to use all the computer RAM today, every last bit of it. We're on to doing means. Means. Count data means 2 categorical variables. That X and Y are both categorical variables. So now we're on to means. Means. Now, when you hear means, you know the distribution is what? As soon as you hear means, we're going to write down all the notation here, but as soon as you hear means, you know the distribution is what? Oh, let me timestamp this. That was a long segment. So formula sheet 1 sample t. As soon as you hear means, you know quantitative and you're dealing with t. So we like to say Mr. T is mean. He's a nice guy, unless you're doing drugs. So we say Mr. T is mean because we're dealing with the t. That means we're dealing with means, and also means are quantitative. Quantitative, however you spell it. Quantitative. It looks good. So we have here that we're dealing with the t distribution, and it's quantitative because we're dealing with means. And you'll notice right here, the first thing we should see is a what? Let's just jump to these. What do we see with these in the formula? Those two things right there. Can you differentiate between them? Those are the first two things we're going to talk about. And we're going to talk about how they're used in problems and what you would see if you saw a y bar or a mu naught. So what are those? What are those? Old memes. That's what they are. I am so blind. Sample mean for y bar. Great job right there, Riona. Great job. This is equal to the sample mean. So this is the sample mean. And a problem would say something like, from a sample of 200 students, we found that the average GPA was 3.7. So the problem is going to say that in a sample, and that's key right there, in a sample, we found a mean of this. So y bar is a sample mean. So it has to always have a sample size. So in a sample of this many students, we found a mean of this. So that is y bar. It can also be sometimes we don't call it x bar, but if you put bar, it literally means mean of that variable. So in more exact language, it's mean of the y variable. So if you had something, someone could say like g bar or s bar, those would just be mean of those variables. You might see elsewhere people do x bar, which is mean of the x variable. So the bar just means mean of that variable. The y variable is the one we're talking about, so mean of the y variable, and it's the sample mean right there. So what is mu naught? So you're on the right track maybe for the next one. So anytime you see a naught, what are you thinking about? We've done a lot of these. So anytime you see a naught, you're probably thinking about a what? We're talking about mu naught here next. We're doing mu naught. Anytime you see that little naught, you're thinking about the what? The null. And that's a great way. Leo's got it right there. It's the null mean. It's the hypothesized according to the null hypothesis. So this is used. Well, we'll do its usage here in a second. We need to insert a mu. I love when sometimes people say, do you know your symbol says Mewtwo? And I say, yep. Symbol for the channel, if you look at it, it says Mewtwo. Haha, I'm a nerd. Rick and Morty. Intellectual. Jokes. Okay. This is the hypothesized mean or null mean. It's like the null hypothesized, what we're theorizing is true. It's just a guess. It can be any number. You just say, I think this is true. So let's go right here. And in its usage, you would see things like, well, mu wouldn't be sample truth. Mu by itself, and we'll do that here next. Priya, great questions. Mu is what? While we write this out right here, you will actually see we use mu, and mu is actually what? And mu naught right here is 3.8, let's say. So mu is the truth. So mu right here is true mean. We don't know this for tests and intervals. So the reason we do these intervals and tests, or population, so true or population mean, that is correct right there. They're synonymous words, but Dr. Seaver, true population, always made us say it that way, true population mean. Why 3.8? Why not? Do you have a different one, Leo? Why 3.8? What can the hypothesized mean be? Remember, you're just hypothesizing something. So what can the hypothesized mean be? No, we'll talk about mu here in a second. What can the hypothesized mean be? You're just hypothesizing. The hypothesized mean, it can be anything. You're saying, I think this is true. Let me just take a guess. And then we'll end up testing that against our sample mean. We'll end up testing that up here. It can be any value. Now, if we use 2, which we could use 2, I'm guessing that we will actually reject the null hypothesis. So I think there's good evidence to suggest that the UT student's GPA, the true UT student's GPA, is not equal to 2. You could hypothesize that, and if we run through the test of this, when we eventually solve some problems with this, we will probably end up rejecting that. I chose 3.8 for a reason, not because I have to, but I think we might not reject that. We'll see when we solve through the problem down here on the bottom, when we create a problem from all this, that we probably won't reject that value. I think I put it in the non-rejection region. I could go a little more safe, and we probably won't reject that, but we'll give this a shot and see if we reject it, because I'm a little fuzzy on if we'll reject that one. We'll find out. But to Priya's question right here, mu is something we don't know. So we do not know the truth. The whole point, I see Tessa got a good question right there. The whole point of a confidence interval is to what the possibility of the truth. By creating a confidence interval, which is what we're doing right here, we have an estimate, and then we get a margin of error, and this interval gives us what's of the truth. Well, we won't know mu here, right here, Priya. We won't know mu. So the whole point of creating, so this is the theory behind it. Like, this is the real, like, I'm trying to get those eye-opening ones. Like, oh, the whole point of creating the confidence interval from the sample mean, which is the estimate of the truth, and we're saying it right there. The whole point of creating a confidence interval is we have an estimate of the truth. So the whole point of the confidence interval is we have an estimate of the truth, and then we're trying to figure out what the truth might be. Do we know the truth? If we are trying to create a confidence interval to estimate the truth, yes or no, do we know the truth? We are trying to create a confidence interval to estimate the truth. Do we know the truth? Do we know the truth? We don't, and we probably never will. We would have to collect data on everybody. So when we read this interval, we would say, I am 95% confident the true mean. We think the true mean might be in here, but we have a certain level of confidence that the true mean might be in that interval. The true mean might not be in that interval, but I am 95% confident that the true mean is contained in that interval. So the true mean is what we're trying to figure out, and we create estimates of what it might be. We're saying I'm 95% confident the true mean is contained in that interval. And so that's what we do with confidence intervals. Does that make sense, Priya, to your question? We don't know what the truth is. We're going to make an interval to say, well, maybe the truth is in this interval. So that's why we create the confidence interval to estimate what the truth might be. And then someone else, this is a different way of doing it though, might say, I think the truth is this. So we would what that value a person gives us. Oh, wait. So Priya, tell me if this helps out here, because we'll do the second one, then we'll loop back to confidence intervals here. If someone said, I think the truth is 3.8, I would say, well, we can what that value. If someone says, I think the value is 3.8, I could say, well, let me what that value for you. Let me what that value. If someone says, I think the value is 3.8, I say, well, we can something that value. We can see if it's true or not, which is what we're going to do here when we work through these equations. I can say, well, we can what it? Think of a 4-letter word, which you have coming up here on Wednesday. We can test it. Does that make sense? We're going to test it. Someone says, I think 3.8 is true. And I say, well, let's test out and see if that looks to be true. Let's see if that's really possible. Let's see what we saw in the population and see, examine it. We're going to test it to see if it is likely to occur. They're just taking a guess. Someone could say, I think UT students are not too bright. I think they have a GPA of 1. Could someone say that to us? And we would say, I reject that. And they say, why? And I say, I ran a statistical test. I have evidence against that. Someone could say, I think UT students are super smart. And I say, I think they're pretty smart. Are they that smart? I mean, I think they are, but I could say, the data might show otherwise. So we hypothesize. So we're not saying mu is this. We're saying we are hypothesizing. Rude. I know. Rude's this right here. I say they're that smart. I have no reason to reject that. I'm not even going to run that test. But we can hypothesize anything. Does that make sense? We can hypothesize any value. Someone can hypothesize UT students have a 4.0 GPA. Someone can hypothesize students have a 1 GPA. And this value that they are hypothesizing is mu naught. Does that make sense? The null hypothesis states that mu equals mu naught. So do we ever know when we do a confidence interval or a test, we do not know the what? Rephrase a little bit there. When we do a hypothesis interval or a test, we do not know what. When we do a confidence interval or a test, we do not know what. Someone can hypothesize we're smart, which you bet we are, or they could be rude to us. We don't want that. We don't know the truth. We're just taking guesses at it. Exactly, Priya. Great job. So when you make this interval, to go back to the interval thing right here, when you make this interval, you're just trying to estimate the what, because you don't know it. We don't know what it is. So this interval right here is trying to estimate what the what might be. We don't know it. Unless we got all the data, we wouldn't know this. We'd have to have data on everyone, which we're not doing right now. We just have a sample. We're estimating the true mean, exactly. We're trying to, and that's what we do right here through this. We either test the true mean. So in a test, you test a true mean, like you're saying, is the true mean equal to this? Or in an interval, you estimate what the true mean might be. Does that make more sense, Priya? So the interval estimates what the true mean might be, and the test tests a hypothesized value someone gives you. They're saying, I think this is true. And you say, well, let's test out to see if that's true. Let's see if that could be true. And then this gives you possible guesses at what it is. And so you think how your guesses and your testing could be connected. We'll see that at the end here, that you could use a confidence interval to see if your mu naught lands in there. Like if your mu naught is outside of it, you could reject it. Where if your mu naught is inside of it, you would not reject it. So you can use a confidence interval to test a value. Priya, 1,000 points. Thank you so much, Priya, Tessa, and everybody. We're here. We don't want to fly through stuff. We got a lot of time. So ask those questions. Because a lot of this is interconnected. I want you to have that really strong understanding. So Priya, 1,000 points. Thank you very much right there. And Tessa, great work too. So with this, I always like make fun. Oh, no, you're wrong, Tessa. If I make fun of students, I'm going to make fun of Florida. Sorry, Florida. But when we get to the 2 sample mean, we'll do a Florida problem. Oh, Florida. I'm sorry. One of these days I got a letter. Stop making fun of Florida. No. Okay. Let's do an easy one. What? It's just fun. It's a joke in the, like, we just, like, you know, it's a joke here at UT. It's a joke to be like Florida this, Florida that, because our rivalry. Pick Bama. Yeah, like either Florida or Bama or something like that. It's Florida's, oh no. It's just in truth, not trying to be mean to Florida. It's just a joke. And so we just it's the rivalry, it's stuff like that. So when I do the 2 samples, sometimes I make a little fun of Florida. So no disrespect to Florida. Very nice state. I've been there before. Didn't go there till in my 30s, almost my 40s, but very nice state. I will say Texas has been treating us very well, and shout outs to HEB. So thank you, Texas. So next one, no, it's just for fun. I've never been there though. Okay, so we got here N. What is N? What is N? Oh, cool, Tessa. I hope you have a great time. What is N? What is in the equation? It's the same thing as previously. N is equal to, I'm gonna do a colon right there. N is equal to sample size. Sample size. We spoke to 200 UT students. Nice and easy right there. Easy peasy. What do we have next right here? Good job, John. We have here the standard error of Y bar. That's just a measurement. One thing, I'm not going to go into too much detail on this. It's just a measurement of variation in the mean. So standard errors, I like to say they're uncertainties. If you take 320 with me, it's the uncertainty of the measurement of a variable created from a sample. It's just your uncertainty. Like your friend says to you, I'll be to your house at 5, but I could be off by about 30 minutes. What's their standard? Now, that's more of a margin of error, but it is still a measure of uncertainty because standard errors are used for margin of errors, but they're kind of telling you some uncertainty in their measurement. Measurement of uncertainty in the mean created from a sample. It's not a standard deviation, it's a standard error, and great job right there. Priya already noting that is the formula. Priya, another 100 points. It is S over square root of N, as you see right here in the formula. So formulaically, which is more important to us right here, the standard error of the sample mean is S over square root of N. So let's insert equation S over square root of N. So S over square root of N right here. Okay, so that is the formula. Probably more important just to recognize it as the formula, and that way we know that is the standard error of the mean, and it's just S over square root of N. I actually made a mistake on a test and didn't divide by N, or square root of N, excuse me. Very common mistake a lot of our students make too. So now that we know what the standard error is, I think we're just a few things away. We just have S, the homework form from last section. Correct. Homework's open till Wednesday. Get those hundreds. S is what? So S is used in this formula. So what is S? S is being used in this formula. So what is S? S is being used in this formula. So what is S? Take a moment, see if you know it. Standard deviation. More explicitly, standard deviation of a sample. Great job right there, Priya. Homeworks they stay open till the test. Homeworks are open till the test. Quizzes close the night they're due. I need to make a video on that or something. Don't worry, Leo, but homeworks you can rework till the test. Quizzes close the night they're due. Sample, standard deviation. Very important to know this comes from a sample. So of the 200 students, the standard deviation of GPA was 0.5. There we go. That's for the sample, though. It's not the standard error yet. You have to do the homework. You have to get an 80% on the homework to open up the 2nd through 5th attempt. So that way, like the quiz, you can get 1 free attempt at the quiz. I should make a video on it. Like, it's a little confusing. It's just to encourage people to do the homework and to practice up for their attempts on the quiz. And the homework really helps. That's the goal, is like you get 1 free attempt at the quiz. So if it's like late night, you can be like, I gotta do the quiz. But if your 2nd through 5th attempt are going to, have you required to do the homework up to 80%, so that way you do the practice on the homework. And the homework is infinite attempts till the test. So get those hundreds on the homework. So someone's hearing this now, go do your homework. Pause this video. Click. Well, if you're live, you can keep watching. Doesn't matter. Okay. I think we only have 2 more things right here. We have T star DF and TDF. Now, as with the previous stuff we were just doing a moment ago, are these the same T statistic? Are these the same? Are those the same T? Is the T star DF the same as TDF? They're different. They are not the same. They're not the same. Reason being is the star means that this is based on your level of what for the interval. The star means this T is explicitly picked based on your level of what for the interval. That star right there means on your level of confidence, like I am this % confidence. That was just given to us, MG. Good question right there. We're not going to find standard deviations by hand, but the standard deviation of 0.5 would be just set for a problem like the standard deviation for the sample was this. So it would be denoted, and that would be the sample standard deviation because it's for a sample. So it would be given to you. We won't find standard deviations by hand. MG, 100 points, great questions. So the star means relative to a certain % confidence, and those are used for confidence intervals. So when you think of the star on a test statistic, it's now called a critical value. And Terry was saying yesterday, it's critical you know these for your % confidence. Kind of like that right there. Pretty good stuff. Good stuff. And so the T star DF. We'll talk about DF here in a second. But this one is equal to critical value used to create confidence interval. The T for a 95% confidence interval with 199 degrees of freedom is 1.98. I think it is. Let's check that. Do I know this one off the top of my head? It's really sad if I start learning the T's. I think that's one's 1.98. We're going to find out here. This is not what you'd be doing on the test, but you'd go here, enter in 199. Oh, and there it is right there. I was close to it. It's 1.972. You're not going to be finding this on the test. We would give you things like this, and you can see right here, confidence interval is the % shaded in the middle, and it's 1.972. I think 100. Well, it's somewhere between there. 199 degrees of freedom. The degrees of freedom control the shape of the distribution, and it approaches the classic 1.96 as degrees of freedom go towards infinity. This would be given to you on the test. We do not expect you to find the T for a certain % confidence. There are other times where you could solve the T with output using equations, but this is the T for a confidence interval, which is given to you relative to the % confidence. We could easily change it right now to say something like 90% confidence, and the T would be 1.653. So the T is relative to how confident we are, which is the % of area we are shading. Now, this applies for t's where there's a star. It also applies for z's where there is a star on the z's, like we were just doing previously on the z's. Check out when we had a z star. That is also the critical value used for a confidence interval, and it's because of the star right here. We're just trying to connect the ideas that when you see the star in the output up here, the star is going to be relative to the confidence interval. Just a quick review of previous topics. Okay, so now we have just the regular old t. For confidence intervals, correct, Leo, correct. Just want to be very clear because someone could say, why did you have us find t? And say, well, that wasn't for a confidence interval. So this, when it has the star relative to a percent confidence, we do give it on the exam. Does that make sense? When it has the star relative to a percent confidence, we would have to say something, use this t to make this confidence interval. Use this z to make a confidence interval. So the star, like, so you'll give us both. So Leo, I want you to rewrite this sentence in the chat, and then I'll say yes to it. So, so you will give us both z and what, so exactly, and Priya's pointing right there. So if you do a small addition to that, I could say yes, those would be given to you. And because here's where I would say no. So this is, yes, Leo, you're right, 100 points, Leo, that is correct. We'd give you T star and Z star, correct. Now TDF right here is the standardized difference between sample mean and hypothesized mean. This gives us a test statistic. This would be something like test. We'll write the problem out. So this is a test statistic right here. And the only other thing to mention right here is degrees of freedom. Noted as DF. For the one sample T, what is the degrees of freedom? What are the degrees of freedom? The degrees of freedom are what? So you don't times this by DF. You don't times it by DF right there. And then this, our problem is 199. That is correct. N minus 1. And you saw how I found it right here. This is N right here. So it's N minus 1. For the one sample T, it's N minus 1. And great job, everyone following along right here. Are N minus 1. So we saw it here where I already solved it. Finding out the degrees of freedom are 199. Now, why degrees of freedom matter? The degrees of freedom matter because it gives you the shape of the distribution. You can see right here, the distribution is like a normal curve at this point, but if you had few degrees of freedom, it's more smashed down. The T looks like the normal, but is kind of more narrow and has thicker tails right here. But when it gets more degrees of freedom, it rises up into the normal. William Gossett, who worked at Guinness Beer, know that story. William Gossett, who worked at Guinness Beer, created this distribution, especially for smaller sample sizes where we don't properly estimate the standard deviation due to the lack of outliers. That's more than you need to know, but you need to know that it uses what are called degrees of freedom to control the shape. The degrees of freedom for the one sample T are N minus 1, so you just go to your sample size of 200 and subtract 1. So 200 minus 1 is 199. Pseudonym is student T because of Ronald Fisher being like, I'm not going to publish your work, beer guy. So his name was also beer guy. So let's do the problems right here on this. Okay. So let's do a section right here. There's the formula sheet. And I'm going to take a note right here because I'm going to try to break up the video a little bit more. So let's say solving a one sample T interval. If I get a question right, I'm getting William Gossett right, William G. So yep, there you go. I know the story of William Gossett quite well at this point. Okay, so we want to create a 95% confidence interval for the true mean GPA of UT students. We sample 200 students, and from this we get a mean of 3.7 and a standard deviation of 0.5. Use a T statistic. If I spell it wrong, my brain can't work. Statistic of 1.972 given to you on test to create the interval. Okay. Oh my gosh, Priya's already got it right there. Oh, Priya, you can already tell what we're going to do to that null hypothesis for the next one right here. So we need to mark our notation. Anytime you get a problem, mark your notation. Great job, Priya. I'm throwing 1,000 points again. Priya, you are doing amazing right here, working ahead, working along, solving the problems as we do them. Now you get to check your work. So we go right here, we mark our notation. 95% confidence is relative to the t statistic given to us right here. So that's the t star df is equal to 1.972. And then we have here the sample size is going to be lowercase n equals to 200. We can solve degrees of freedom just for fun is equal to 199. Remember, it's n minus 1. Great job right there. Oh, that's already pre-put it twice. So correction. Oh, correction. Oh, did you do 3.8? Oh, so we are going to reject that. Find out more here in a moment on that. And then we have the sample mean in here. There it is. Yeah, I noticed that too. I noticed you used 3.8 as a Y bar. And it's gonna be the same interval, just centered it. You moved the center, you just moved the center down. Does that make sense? The margin of error did not change from 0.0697. Yeah, see if you can. So I already know the margin of error for this interval. And Y bar is 3.7. Let's solve the interval over here in a nice blue pen. So now that we have all of our notation, good to see you here, Dem. And we're going to go here, Y bar plus or minus T star df S over square root of n. Go ahead and try to interpret this if you want. Great job, Priya, right there. The margin of error is everything right here. So this is the margin of error. This is the estimate of the truth. So that's our estimate of mu. We're trying to guess at mu, right? We're saying, well, maybe, what's the truth? What can be the truth? Try to interpret the interval if you're practicing along right here. Okay. So now, look at that. We just write in the numbers. 3.7 plus or minus 1.972. And then S is 0.5 over square root 200. Okay, let's take a look. 200 square root, copy 0.5 divided by, there we go. This is the standard error right there. So that's the standard error. We're going to times it by this for the margin of error. There we go, 0.069. Great job. Priya's got the same number. So that means I can look at the screen right here, plus or minus, so 3.7 plus or minus 0. I'm going to round this, Priya, to 0.07. That makes the numbers nice and neat. So I've rounded it. Don't round to your final answers. Maybe it says report to 2 digits. So we'll pretend the problem says that. And now if you take a look at this, we would get a lower bound of 3.63 and an upper bound of 3.77. So the margin of error has been confirmed to be this right here. This is the margin of error. Look how it goes up this amount and it goes down this amount. It's a plus or minus around the 3.7, which is at the center, plus or minus the margin of error on it. So that's right there. Great job right there. Leo also practicing along. Then how would you interpret this interval? How would you interpret this interval? How would you interpret it? I am. We have our interpretations from yesterday. Well, we can just copy it from the previous one. I am blank % confident that the true blank is contained in the interval blank to blank. Here it is right here. I am blank % confident that the true blank is contained in the interval blank to blank. So how are we going to interpret this? I am blank % confident that the true blank, and that's usually where mistakes are made, especially on the 2 sample t. If you want me to say something that will help you, the 2 sample t is when we're talking about the true difference between the means between blank and blank. That's where people make mistakes. It's usually the 2 sample t they have problems interpreting. That can be on the test. Wink, wink. I am 95% confident the true mean of GPA of students is contained in the interval. Great job right there. MG and Priya and everybody looks great job. Great job. That is it. I am 95% confident the true mean of GPA of UT students is contained in the interval 3.63 to 3.77. That's got it. Now we're going to do the test on this. So let's put a new segment in the video. That's a little quick segment right there. 3140, solving a 1 sample t test. And so let's go over here and solve the 1 sample t test. Okay. Great job right there, Zachary. The mean of GPA of great job. Okay, so the one sample t-test is going to be when we say we want to see if the true mean GPA of UT students is 3.8 or not 3.8. That right there is truly, you could say, is truly, let's say this, is truly 3.8. This implies that there is no sidedness to this test. What do we mean by sidedness? We could say something like this. We want to see if the true mean GPA of UT students is higher than 3.8. That's going to be a right-tailed test. When we say greater than, we could say lower than. That's a left-tailed test. Or if you just say is 3.8 right here, there's no sidedness. We're just seeing if it is this. This is going to be important when looking at a test to figure out the sign of the alternative. So the sidedness, greater than, less than, or does not equals to, is going to indicate the sign of the alternative. So make sure to read the researcher's question, not the data, to know the sign of the alternative, whether it's greater than, less than, or not equal to. I'm mirror image, so greater than, less than, or not equal to. I know my left from my right. I'm mirror imaged. Someone's like, what are you doing? You don't know your... We speak to 200 UT students, and from this sample, we find a mean of 3.7 and a standard, great job right there, deviation of 0.5. Run the hypothesis test below, doing all 4 steps. Now, you're not going to be doing it quite like this on the test. It's more questions in individual parts. So when you look at this right here, we're going to do all 4 steps, but make sure you know the steps in the process. And Priya's already started us off there for 100 points by writing the null hypothesis. Step number 1 is going to be to write your null and alternative hypothesis. Step 1 right here, write the null and alternative hypothesis. So let's write the null and alternative, and Priya's done a great job right there writing the null is mu equals 3.8. So the null hypothesis, which is assumed to be true, kind of crazy, right? We're going to write here HO, which is null, and then we're going to insert mu sign right here, insert symbol, mu equals 3.8. Now, why is it 3.8? What about this equation, Priya, that when we do this, why are we putting 3.8 right here? Why would 3.8 go right there? Because in this spot right here, it's always the hypothesized value. Does that make sense? We're always saying the truth is equal to what we think it is. I know that sounds crazy to be like, the truth is what I think it is. Well, that's what you're testing. You're testing if the truth is what you think it is. That's what you say, here's what I believe, and let's see if I should reject that. So in the null has the equal sign test, so you are correct. The null always has the equal sign because we're saying, here's what I currently think. I hold this as truth in my head, that this is the true value of the mean. We're not saying it is this. We're hypothesizing it's this. This is our current initial belief. So it's not that mu is this. It's that we currently believe this. Does that make sense? Like, imagine you have a friend who's super full of themselves, and they say, I think I can do 100 push-ups. So right now, their null hypothesis is push-ups they can do equals 100. And then you could say to them, I have an alternative that you can't do 100 push-ups. So, or you can do less than 100 push-ups is your alternative. I say, my alternative is that you can do less than 100 push-ups. So what could you do, think of a 4-letter word, to see if they really could do 100 push-ups? They're like, I can do 100 push-ups. And you say, okay, let's put this to the what? Let's put this to a what to see if you should continue to believe the null. Let's put this to the test. And then you would either have evidence they can't do it, or they could continue to believe that they can afterwards. That's how we do it statistically speaking. You wouldn't prove the null. You would just say, okay, it looks like you were right to believe that. You shouldn't reject that. You should continue believing you can do 100 push-ups. If they did something like what if they did? Imagine they do 99 push-ups. Would you at this point reject the null hypothesis in the way we do statistics? This is where I want your stats mind to be on. If they did a 99 push-ups, is that a good enough amount of evidence? We haven't run a test right here, but I just want you to think of how the stats world does this. Do you think that would be enough evidence? Probably not enough evidence. You're like, well, maybe you can do 100 push-ups. Like, I don't know, maybe and we're talking good push-ups. We're talking some good ones right here. They're going all the way, and then that 100, they're like, oh, You're like, maybe you can. I don't know. That was close. I mean, maybe you can. Maybe if you did it again another day, maybe you could. So this is what we're doing right here is we're seeing, someone says, I believe the mean is this. They just say, that's what I think this is. To reiterate again, what can mu naught be? We're making sure people understand the whole point of mu naught. What can mu naught be? Here, watch this. Can it be this? Can I do that? Because what can mu naught be? It's just a belief, right? So mu naught can be what? Can be anything. Can be any belief you have. Any initial held belief by anybody. Probably values that are logically possible, as Leo's putting right there. Great job, Leo, there. Someone said, what if someone said, I think the GPA of UT students is 100. What do you think would end up happening to this value? They say, I think they have 100 GPA. And you're like, it's not really how GPAs work. We probably don't even need statistics in this because I'm pretty sure I can what that value. Like, we don't even really need stats for that because I'm pretty sure I can what that value. You say, you think UT students have 100 GPA? I can reject that. That's just not even possible. And that's what the p-value is going to tell us if this belief is possible. That's why we do p-values, to tell us how probable or possible certain values are. So someone says, I think it's a 3.8. And we say, well, let's test this. And the alternative right here is going to be based on the researcher's question. And we have a researcher asking if it is 3.8. So the alternative right here would be it's not 3.8. So the null is, well, is it 3.8? Maddie, good to see you here. Oh, that's awesome. Oh, Maddie, drop the, yeah, of course I remember Maddie. Drop a question in the chat. What are you working on? We'll do that here, probably maybe between a question right here. Drop it in here. Take another stats class. That's so super cool. What stats class are you taking? Drop it in the chat, Maddie. We'll finish off this one, and then we'll do your question, especially Maddie. Let us know. Okay, step 2 is to do what? Now that we have this, what is the, well, right here, we have the sample mean. I think Priya's solving the problem as we do this. Here's the sample mean, here's the sample size, here's the standard deviation. So this right here, we'll highlight it in green. That's the sample size. That's the sample mean. And that's the standard deviation of the sample. So now find the t, z, or chi-squared. What is the, oh, like in real? I think we have like a 3.6 GPA or 3.6 maybe. I don't know. It's a good question, Priya, right there. I don't know for real. It's a good question. Okay, so now the general partner of Limited has told me, a potential investor, that the mean monthly real estate. Okay, yeah, Maddie, keep putting it in here. As long as I can work, as long as you can say you can work this isn't like some sort of, yeah, I think as long as you're given, this is something I can ask on the stream and you can solve. And we'll take a look right here at Maddie's question. It might actually relate to what we're doing. It might actually relate, as long as you say you are allowed to solve this, Brian, or talk about it. So as long as you say you're allowed to solve it, just want to make sure. Okay. This is literally what we're doing right here. She obtains the monthly rental charges for a random sample of 36 three-bedroom homes in order to test the null hypothesis that the true mean is 500 against the alternative that is not 500 with an alpha level of 50%. The sample mean is 520 with a standard. This is literally the question we're doing. Maddie, it's a practice exam question, so it should be all good. Okay. This is literally what we're doing right here, Maddie. You came in at the perfect time. 1,000 points, Maddie. This is literally what we're doing. This is a one sample t-test. That is a one sample t-test. Yeah, that's exactly what we're doing right here. Let me see. Let me try to do it really quick, and then we'll finish our problem. What was the standard deviation? It was a standard deviation of $48. Sample size of 36. That's 6 divided by 48. 48 divided by 6 is wait, my brain's breaking. That's it's 8, right? Yeah, it's 8. It's 8. The difference was 500, 520. That's 20 divided by 8. The t-statistic is 2.5. With a t-statistic of 2.5, you're doing the does not equals test. 3.65. The p-value is going to be about 0.02. It looks like you're definitely rejecting the null hypothesis. It looks like the p-value is something like p-value about this right here, and reject null. We'll do that here in a second, and I'll show how to solve it. And then people use sometimes H0, H1. So let's take a look right here. I think it's a T of about 2.5, p-value 0.0145, something close to that. The p-value is a little hard to estimate, reject null hypothesis. Let's take a look. We'll solve that here in a second. So now we're going to find the t-statistic. So Maddie, try to solve this along with us here. You might actually solve your problem while doing this. So what you need to identify in your problem, Maddie, is the what? What do you need to identify to solve? Because this is the step we're on, Maddie. I want you to try to solve your problem here with us too right now. What do you need to identify? What do you need to identify in your problem right now? So try solving your equation right here and see if you get the same answers I do, because I was doing it in my head. What do you need to identify right here? Your what? And Leo knows it.
Notation, brother.
We need to find the notation. So in your problem, Maddie, we're going to find the t, but we need to find the notation first. So in your problem, Maddie, the sample mean, which is y bar, was 520. So your problem has a sample mean of 520. Your problem has a hypothesized mean of 500. Your problem has a standard deviation of 48. Your problem has a sample size of 36. Does that make sense, Maddie? Do you have all the notation written down for your problem? Like, write it down the following way. Let's do this right here. We're going to do it for ours. Our problem said we spoke to 200 students. Our problem said the standard deviation was equal to 0.5. Our problem said the hypothesized mean is equal to 3.8. Our problem said the sample mean is equal to 3.7. And I think that's it. Next, we need to know degrees of freedom. This is the one sample t. That's the last bit of notation. Maddie's problem had 36 sample size. Our problem had 200. Feel free to tell us either degrees of freedom right here. So we're writing down all of our notation right now. Our problem has 200. Remember, we're doing the one sample t. So what are the degrees of freedom? So our problem has, it's 199. It's just n minus 1. So Maddie, what are your degrees of freedom for your problem? What are your degrees of freedom for your problem? Your problem has degrees of freedom equal to what? Your problem has degrees of freedom 35. There you go. And we'll be using that here in a second. So now we're going to solve. So you already have your null hypothesis written for your step 1. Next, we need to solve for the t or the z or the chi-squared. Now, we're doing t because Mr. T is mean. He's a nice guy, but if you're doing drugs, he's pretty mean. And we say this, Mr. T is mean, because it remembers the t distribution is for the mean. So now let's go ahead here and solve for the t statistic. The t statistic is going to be t with degrees of freedom, we already found what it is, but that tells us the shape, is equal to the sample mean minus the hypothesized mean over the standard deviation over square root of n. That bottom portion there is the standard error. We just usually write it fully out. I prefer to. And now let's go ahead and solve in 3.7 minus 3.8, which is just the difference. And then we're going to standardize that difference to give it context. And the standardized difference right here over square root 200. There we go. And let's solve. 0.5. Well, got to do it the other way. 200. Has anyone solved this yet? There we go. And let's take right here and do 3.7 minus 3.8. Divide by, and there's our t statistic. Great job, Pri, 100 points. Maddie, do you have your t statistic now? So Maddie, did you get, there's no t star right here because remember the star is for percent confidence. So there's no t star for this one because now we're just doing solving for the standardized difference. In a t-test, which this is a t-test, not a t-interval, we take the difference up top between what we see in the sample and hypothesize, and then we standardize it to give it context. This standardized difference is what gives you a test statistic right here. No worries. Stars for confidence. And Leo, great practice right there. The stars for the confidence. So, Maddie, do you have your t statistic that you need? Did you find 2.5? Is that correct? Tell me if you found your t statistic, Maddie. If not, I'll plug in some numbers right here. But did you find your t statistic? We'll in here from Maddie. Did you find your t statistic? No. I hate that it does that. What is your calculator? Well, no. What is your calculator giving you for your problem, Maddie? What does your calculator say for your problem? I think it's 2.5 also, Maddie. Are you... Well, that's the t? Well, that might be the p-value here or something. We just have the t right now, so you should just have the t statistic. Does that make sense? You should just have a t statistic right now. That might be the p-value they found, Maddie. I might have been way off in my p-value estimates. We'll check that out here in a moment. But should be 2.5. Oh, your calculator is wrong? I do. What you should have for yours. Should have. Sample mean, yeah. Difference. I should be right there. Yeah. So we are getting 2.5 right here. We are getting 2.5 for yours, Maddie. Double check and yeah, grab a calculator if you can, like a one from a friend or something, to solve these. But yeah, grab a TIs preferably, but any calculator works as long as you know how to use it. I have people who grab TIs who then don't know how to use them, and then they don't do well because if you have a calculator don't know how to use, it's not good times. It's not. 2 seconds here. Gonna make it so I can move it. Okay, so now we're gonna solve. What do we need to find now, everybody? Which this would be, moreover, given to you on the test. What do we need to solve for now? Now that we have this, what do we need to solve for? We have our t, so what's our next step right here? After we have our t, we're gonna find the what now? P-value. So now let's find the p-value. So find the p-value. Now, this is one, I might do it a little quickly here. Not really great for our test because we don't have you do versus scientific calculator. Yeah. Great job right there, Tessa. Thank you, Tessa, right there. Tell me what the difference is. Here's the t distribution, 199 degrees of freedom. We're doing the two-tailed test. Our t statistic was negative 2.828. And we put it in, and we get a p-value of 0.005. 0.005. Does that make sense? 0.005. 0.005. So think about this. Although 3.8 is not that far away, the p-value of 0.005 tells us that we saw was what given the null is true. What we saw in this was very what given the null is true. And Zach's on the right track right here. But you will have to solve for these right here, Leo. You could have to solve for these. These are T's you will or could have to solve for. P-values, not so much. P-values, not so much. And as Priya's pointing out, that P-value is low. That P-value is low, and thus we would reject the null. And I did this portion quickly because this is less test relevant. Hence, we focused more on this right here. The things we focus more on, yes, p-value, correct there, Leo. P-value is not so much because you would need applets. You do need to know degrees of freedom when we use the t-distribution. P-value is not so much. We could give you pictures or stuff, but don't expect to be going to applets or things that would require the applet to be used. Now, the fourth step right here is to do what? The fourth step is to do what? We're on to step 4 now. And step 4 is what? Oh, we almost got it all on one page. Step 4 is to do what? Gotta zoom in on it. It's like 40-ish. It's similar to length in other exams. I think 40-ish, something like that. So what do we do right here? Oh, well, we got it highlighted. Our p-value is low. And Leo's, thank you, Leo. I take guesses. I'm like, I think it's 40, and it is 40. There we go. So our p-value here is low, so we reject the null, right? Our p-value is low, so we reject the null. And so we just need to say, I reject the null hypothesis. Take a moment. Try to write this out. This is on the test. Write it out in the chat right now. There's no more coffee in this. I checked. No more coffee. If there was coffee, there wouldn't be anyways. Oh, well, thank you so much, Maddie. I love stats. People think I'm crazy. I was walking by Spider-Man one time, first Spider-Man movie. These people were like, I hate stats. And I was like, you hate stats? And they're like, yeah, I'm taking it right now. And they were like taking it at a different thing. And I was like, I'm sorry. And they're like, who are you? And I was like, I teach stats. They literally say I hate stats. Majed, good to see you. I know, right? I kind of have to for comedic purposes. Take a moment here and try to interpret this. I was like, if it lands on my face, I'm like, it'll at least be a little funny. Get something out of that last drop. Back from for some review. Nice, Majed. We're back interpreting. We're doing the formula sheet, every little bit of it, knowing how to do each thing on it. So what would we say for this one? Take a look if you haven't seen the start of this. We were testing the true mean. What you really need right now is you need the null and alternative. If you're stuck on this, the only thing you need are the p-value and the null hypothesis, which we said the true mean is equal to 3.8. And the alternative is that the true mean is not equal to 3.8. And with this information, you can solve this. I reject the null hypothesis that the true mean of GPA is 3.8 at the alpha level 0.05 with a p-value of 0.005. This means I do have evidence from alternative that the true mean... Yeah, MG, I'm throwing you 1,000 points right there. I'll take the caps lock. We don't mind it here. We're just like, we're shouting those answers. Great job, MG. That is 100% or 1,000% correct right there. I reject the null hypothesis that the true mean of GPA, you're just reading this off. I reject the null hypothesis that the true mean of GPA is equal to 3.8 at the 0.05 alpha level right there with a p-value of, and there's your p-value. This means I do, and we're going down the first road right here, have evidence for my alternative that the true mean of GPA is not 3.8. Great job right there and great practice. That was your fault. I reject the null hypothesis. That's what I mean. And not the states part. That's all right there. I'd probably, if I have greater, wouldn't want them to take off. That's not that big of a deal, Tessa. I reject the null hypothesis that the true mean of GPA, but that does say the null hypothesis states. Like this right here says the null hypothesis states, but usually when we do the interpretation, we'd say, you know, the null hypothesis is the true mean of GPA is 3.8. I reject, and then I would, Zachary, I would not put in statistical notation like when you're, so Zachary, 100 points right here. On the test, I wouldn't use the stats notation for it. I probably would give you full points. Watch out, because some graders might not. Look at the way. Got to give shout outs to MG right there. MG starting us off strong right there with a perfect answer. I reject the null hypothesis that the true mean GPA of students is 3.8 at the 0.05 alpha level with a p-value of 0.005. This means I do have evidence from my alternative that the true mean of GPA isn't 3.8. That is A+ right there, MG. Great work. And so we're going to just talk to someone like it's a sentence, like, yeah, that 3.8 value, toss it out. We got evidence it's not 3.8. It's very unlikely what we saw with our sample. You're welcome. We're going to head over to the next one, and everyone, let me type that. That 200 character limit stopping us right here. Let's do the next thing, the 2 sample mean. Here we go. Huge shout outs. This is some really good practice. Thank you everyone for being here. We're jumping over to the 2 sample T now. Then we got some chi-square test of independence to finish off. We're literally, each day I think we're pretty much going through the whole last portion of the class. Like these 3-hour streams are basically reteaching in a certain way, like everything. Yeah, I know. I think Sunday we'll have a lot of people, or we, don't tell anyone, but we'll probably do something on Wednesday. I usually do something the night before the exam. But there's a lot of exams. People probably have, marketing, economics, finance. There's some really tough exams. The exams are the hardest part of pretty much any class. So if you have an exam on Monday, totally understand if you're right now studying up for that exam. Gotta handle what comes first. And so, but thank you to the 14 people here just relaxing, chilling, as we're about to do the formula sheet, the 2 sample T, right? The 2 sample T, that's correct. 7 something. What time? I think 6:30, right? Someone wants to check. Please tell me if you have any conflicts. Okay. Oh my gosh, Tessa, I'm sorry. Man, I didn't feel anxiety. F5 finals. MG, I'm sorry. I didn't feel anxiety till I took a math class and the professor was really mean. And then I actually got test anxiety. Like, I didn't get test anxiety till I was like 35. What's up with that? It's because the professor was mean to me. I swear the guy hated me. Oh, anyways. Enough life stories with Brian right here. Chemistry final. Whew, that sounds tough. Okay. Let's head over and do the 2 sample mean and start talking about what's on the formula sheet. Here we go. Well, let's study up here and let's diminish our worry by understanding all the notation. Now, once again, a lot of these problems are really going to come down to knowing the notation. So when you look at the formula sheet right here, let's start it off. Okay, the 2 sample t-test is called why? The 2 sample t-test. Why do we call it the 2 sample t-test? Why? Kind of like that. Why do you call it the 2 sample t-test? Why is it called the 2 sample t-test? And if you subtract something of 0, that doesn't really matter. I don't usually include that. It's just superfluous information. It has 2 means. Correct, Priya? Not just 2 means. Not just 2 means. Not just 2 means. Because the other one has 2 means. This one doesn't have Jaren, great to see her. It doesn't just have 2 means. It has 2 sample means. Oh my gosh. It has 2 sample means. It has 2, and so you have a sample size for one, a sample standard deviation for another, a sample mean for one, sample standard deviation for another. So it has 2 samples. Very important to know. And Leo, we were talking about this earlier. So great stuff. Leo asking some great questions as always, and Priya and Leo and Majed right here. Majed and Tessa, so good to have you here. When you do the 2 sample mean, you are analyzing a quantitative y variable. And then there is a 2-level categorical x variable. So you're breaking it apart. You're just comparing 2 groups. That's the point of a 2 sample t-test, is to compare 2 groups. So this is where we do our Florida UT students to compare the GPAs of those students. Or we could say a test. We'll give them a test. Okay. So y bar 1, y bar 2. How would you describe those? Y bar 1, y bar 2. Oh, Priya never got her level? Let me go insert that right now really quick. Sorry, you're right. We didn't do that yesterday. Fixing that really quick right here. What is y bar 1, y bar 2? What is y bar 1? What is y bar 2? What is y bar 1? What is y bar 2? I think we have it fixed now. Check your points here in a moment again, Priya. What is y bar 1, y bar 2? Y bar is the sample mean. Go a little more specific. Y bar 1, y bar 2. Y bar 1, y bar 2 is... There we go. Oh, we did have to do... It's a lot to write this one. Y bar 1 is equal to... Oh, did I... Oh, you're almost there. Wait. Oh, it should be. Did not update? Priya, try again in a moment here. It should be updating. Mubot sometimes takes a little bit to update. Try again. It should be there unless I made a mistake on it. I think Priya's reached it. I don't know if you have yet, Leo. I think you have. Priya's reached it, but not you, Leo. Sorry, Leo. Priya level. First one to reach it would be Priya right here. Or you might have. I think you have. There we go. Oh, no. Maybe I'll change it so your Priya's the only one at it right now. But there we go, right there. It is updated right there. I put it to 320,000, but apparently you both reached it. So right, we're gonna make it so the only person at it right now is Priya. Here, wait, Priya. It might take me a moment to update. Leo's still gonna be at the Leo level. There we go. Correct. 5, that is correct. You're welcome, Priya. Thank you so much. It's being here, helping out, that makes chat. So I want little rewards, little fun stuff right there. We love it. So we have the sample mean of group 1. Here, we'll get serious right here. The sample mean of group 2. We found UT students scored a 94 on the exam. We found Florida students scored an 84 on the exam. Okay, so these are the sample means for each group, and we're then going to be comparing these. Does that make sense? The whole point of this is to look at the what between the two means. The whole point of a two-sample t-test is to look at the what between these two means. The whole point of it is to look at the difference between these two means. So you can even be thinking about this. What if I told you I only sampled 2 students? A difference of 10 might not be significant because that's a lot of uncertainty. You'd be like, you only talked to 2 students and you found an average of 94, and 2 students found an average of an 84, like 2 students here, 2 students here, sample sizes of 2 for each group. Then the difference might not be statistically significant. What if I told you this was from 1,000 students at each school, which is less than 10%? Then the difference of 10 might be statistically significant. It would be. So with this, because I've done a lot of problems, I know it will be. With this right here, let's look at the remainder of this. And we're going to highlight this in yellow because these are the examples we're talking about. What else do we need for these groups? Just theoretically speaking, if you're going to compare between groups, what else do you need between these groups? You wouldn't just need it's a video game. You wouldn't just need the sample means. You would need what? You would need the sample sizes. Great job right there. Now, do the sample sizes need to be the same? Yes or no? Do the sample sizes need to be the same? Do the sample sizes need to be the same? Yes or no? No. Great job, Priya. I was trying to trick you right here. I was trying to trick you. If you said yes, don't worry. 100 points. Everyone got it right still. They don't need to be the same. That's just math. It'll solve. So they don't need to be the same. I was just trying to trick you by putting them as the same. They can be. They often are if you do like equal samples of each group. They don't have to be. As The Rock always says, it doesn't matter. Sample sizes can be different. They don't need to be the same. So that's just how many students we speak to from each group. What else do we need right here? There we go. Oh my gosh. Leo, 100 points right there. What else do we need now? We don't just need the sample sizes for each group. We need the what for each group. We don't just need the sample sizes for each group. We need the what's for each group. So we're just going through the notation right here, trying to figure it all out, the standard deviations. So we're just going to take and copy this down and just change these to S's right here. Not like that. There we go. And there's this standard deviation. The sample standard, probably could just write out, deviation of group 1. We saw a standard deviation of 0.45. There we go. And we'll just copy this. For UT, for Florida. Good. And highlight. These are the contexts, like where we're using it in context, and just showing what it would look like in a problem, and then what the general notation of it looks like for this right here. So that's the standard deviation of group 2. Oh, it capitalized it. That's really. Oh, it just doesn't want to do it. There we go. Okay. Good. These are the standard deviations right there. And then now we just need to talk about two more concepts. Okay, so as we've been saying throughout this whole thing, are these t statistics here the same value? Is that t and this t the same? Are both of those t the same? Are those t's right there the same? The t star df and the tdf? No, Zach, no, those are not the same. What's the important thing to see with the T star DF? The T star DF has a what telling you your level of what. The T star is for confidence given to you by the problem relative to percent confidence. The T down here is a test statistic, which is a standardized difference. The difference between the two sample means divided by the standard error gives you a t star right there. The difference between the TDF is the difference standardized. The T star DF has a star because it's relative to percent confidence. Brian.exe had critical error right there. Okay. The standard errors right here are the measurement of variation. This is called the standard error of the difference. I guess we'll write it the way it's written. So we'll write this right here. Can I do a subscript? I can't. It's written as subscript up there, but this is not an equation. This right here is the standard error of the difference. So this is a measurement of variation within the sample means differences. Conceptually, that's what it is. I mean, you will have to solve like s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. This value right here, which is seen right here and right here, is the value. It's the same value. Those are the same. So it's just showing you how to solve it. So that is the standard error. Great job. Priya's already found our standard error of the difference right there. So that is a measurement of variation which will be used. It's used both in the confidence interval and both in the test, bringing us to some analogous concepts when we look at the test to see if there is a difference. Okay, so we understand what that is, and I think we've got everything. So now we can start doing some questions. Oh, we got one last thing. Degrees of freedom. The degrees of freedom are what? What are the degrees of freedom? Who knows, for the 2 sample T, what are the degrees of freedom? The degrees of freedom are what? Someone's probably said it in the chat now, but the degrees of freedom for the 2 sample T, we like to say in our class, are 2 what? So the degrees of freedom, which tell us which T we are using, the degrees of freedom are 2 complicated. They give us the shape of the distribution. There's the degrees of freedom, and we just say this is 2 complicated. You will not solve for this on the test. The degrees of freedom for the 1 sample T is n minus 1. The degrees of freedom for the 2 sample T is 2 complicated. There's the degrees of freedom for the 1 sample T, which we were covering just a little while ago, n minus 1. And the degrees of freedom for the 2 sample T is a 2 complicated formula. We'll use like jump output, but we say it's 2 complicated. Don't solve this out. This is 2 complicated. So that brings us to the problems right here. We spoke to this many students. We saw these standard deviations, and now we can actually run the tests and do the intervals. So let's take a look at the tests and the intervals right here. So we'll do a new section on doing the interval. So 2 sample T interval. So 2 sample, let's go solving a 2 sample T interval. And here we go. We're looking at the jump output. What will the degrees from look like? Great question. We'll look at some jump output on this too here at the end. Good question, Zachary. Actually, I might have one open. The degrees of freedom will be right here. There it is right there. DF, degrees of freedom are right there. So does that make sense, Zach, right there? No, but I mean, like, that's the degrees of freedom. There's the difference between the sample means and the output. There's the standard error we were talking about. So that's y bar 1 minus y bar 2. There's the standard error. There's the T statistic. And that's not the T used for the confidence interval, though. So great questions there, Zach. And it does, the degrees of freedom does give us the shape of the distribution that we are using. So in this problem right here, we went out and spoke to 100 UT students and 150 Florida students. From this sample, we saw a mean for UT of 94 on the test and a mean for Florida of 84 on the test. Their standard deviations, gotta look at what I put down here again, 0.5, 0.5. And these don't have to be the same, but I did it for ease of use. Their standard deviations were both 0.5. create a 95% confidence interval to estimate the true difference between the means. Okay, so this interval right here, often people interpret this interval wrong. I usually see a lot of wrong interpretations on this interval. So let's go ahead and solve this right here. First, marking our notation. It's the same notation from the previous problem, but we'll put it over here on the side. First, let's highlight the numbers right here. And these are the numbers we're marking down. And we need the use a t of, and we got to find the t for this. I'm doing this because this would be given to you on the test. It's going to be degrees of freedom like 224 or so. We'll find out. Once again, this would be given to you. So 100, 150, I say 224 degrees of freedom. 212 degrees of freedom. And now we go back over here to the applet. And let's go right here and drop this in. And now 95% confidence. And it's 1.971. 1.971. And that is going to be the degrees of freedom right there for the the two sample t. Excuse me, the degrees of freedom are 2.212, and the t statistic we're using is 1.971, given to you on the test. Use a t of 1.971. Okay. Now that we have all of our notation, we're going to go in here and we're going to mark it down. So try to mark the notation with me as we do this. We have right here that sample size 1 is equal to 100. Sample size 2 is equal to 150. Mean 1, which is the mean of UT we're using that for, is equal to 94. Mean 2 is equal to 84. Standard deviation 1 and standard deviation 2 are both equal to 0.5 and 0.5. There we go. That's all the notation. Now it just comes down to solving the problem of, great job, 61. I don't know. Oh my God. I think Leo got the T statistic for the test, Leo. That's a difference, right? So Priya might have the interval right here. And then we need the T. Priya might have the interval. That's a T star. And so y bar 1 minus y bar 2. Yeah, no worries. I bet you got Leo 100 points, Priya 100 points. It looks like, yeah, your numbers look correct right there, Leo. I can estimate the standard error from this, especially from Priya's interval. I could find the standard error. We'll find out, Zachary. So if we're doing the interval right here, we're making a 95% confidence interval right here, right? So we need to first find out the what of our interval. If you make a confidence interval, I would first calculate the what for your interval. What would I first calculate? Here's the estimate of the difference, which is pretty easy to see. That's just the estimate of the difference right here. So this is the estimate if you subtract those. And then we need to also get a margin of error. So we will get the standard error. And then this is the critical value right here based on the level of confidence. And this all equals the margin of error. Like that whole thing is the margin of error. So you do find the standard error. No worries, no worries. And so we find the standard error first to then times that by the critical value right there to give it the confidence level. So we're going to solve these numbers right here. There we go. Okay, we're going to solve for the standard error first. The standard error should be about 0.065. Should be about that. Okay, let's go ahead and solve this right here. See if I was right in my estimate. There's that first portion right there. Is that? There we go. It rounds to that. There we go. And I was using the numbers you gave, Priya, to estimate it, looking at your intervals, like, okay, the margin of error is this, the standard error should be about this. So that is the number right there for the standard error. Solve out your mathematics. Make sure you get the same number here. We multiply by 1.971 to get the standard error. I mean, the margin of error, that will be 0.1272. So let's try this, and we should get 0.1272. So 1.971, and there it is, 1.272. Great work. And I'm using Priya's answers to figure it out because Priya kind of showed me via her interval what the margin of error is, because I know 10's at the center, so I can look at that and say the margin of error. If you're looking at Priya's interval, I know the center of this interval is at 10, and then Priya said the upper bound is that, so I know she went up 0.1272. So if you're wondering how did I figure that out, I used it from the information I was given. And it helps me check my work right there. Thank you, Priya. As always, 1,000 points, Priya. Keep it up. Keep the practice up. Great work for the test. So now what I usually do is I express this interval as 10 plus or minus 0.1272. Now, here's the thing. Interpret this interval. We always do this right here. Take a moment. This is where people are going to make mistakes, and we're going to round this. So interpret it. This is where people have trouble interpreting this one. So this is one people get wrong all the time. For the test, you might have got that for the test statistic. We've already done all the work to do the test. Yep, that's the test statistic, because we already know the standard error, so I just divided the difference by the standard error. If you start to realize the patterns of these, I just solved the test statistic, and you are correct. It's 154.92. And then we'd know the p-value, and we could reject, fail, reject the null. And you can also look at the interval to do the test. At this point, we're interpreting the intervals, so take a moment right here. This one is the one usually people get wrong right here. This is the interval that people have trouble interpreting. And I want you to think what we're interpreting. Just see if it makes sense when you interpret it. I know Priya's just got all the answers. So interpret this interval and then see if it makes sense when you interpret it. Interpret the interval, see if it makes sense. This is where people make errors. And it's all right. Any thoughts? I am blank % confident that the true what? So think what we're talking about here. This is the hard part for people. This is where points are lost on this one. What are we talking about? What did we analyze? So this is the context. This is where usually points are lost right here. We're trying to analyze what for this? What are we trying to analyze? And the first part of the interval is what you're trying to analyze. So we're just taking a moment. I'm trying to tell you as honestly as I can. When I read interpretations, the interpretation of the two sample t interval, the interpretation of the two sample t interval is what? I am 95% confident, kind of. Very close, Zachary. Zachary, good job right there. That's kind of very close. Not the sample means, because we know, and Priya, good answers right there. We know the sample mean difference is 10. So we know what the sample mean difference is. So you're super close. We know what the sample mean difference is. We observe a sample mean difference of 10. We observe a sample mean difference of 10. So we know what the sample mean difference is. I am 95% confidence that the true difference between the mean score of the test for UT students and Florida students, because that's what we're trying to figure out. We have a sample difference, right? So we're trying to figure out the true difference. I am 95% confident that the true difference in means for tests for UT students and Florida students is contained in the interval 9.87 to 10.13. That is exactly right there. And so when we do this right here, we would say, I am blank percent confident that the true mean difference between UT and Florida students is contained in the interval blank to blank. Awesome work right there. And then let's see what else right here. Well, that's got it. I want you to notice something real quick. And I'm going to take a real quick, I'm going to make my second cup of coffee. So take a real quick break right here. I am 95% confident that the true mean GPA, the true difference in means for the GPA of, and we're not doing GPA, sorry, we keep saying GPA. This was a test they took. The true difference between mean test scores of Florida students and UT students. So let me write that in right here. For this one, we would say the true difference between the mean of group 1 and group 2. So this one right here, exactly, I think that's going to help out. I am 95% confident that the true difference between the mean of group 1 and group 2. The true difference between the mean of group 1 and group 2. And we could say, since the interval is blank, this is evidence blank is higher. So think what you would say right here. Since the interval is positive, this is evidence UT has what? Since the interval is completely positive, or you could say, we should do an alternatives right here. Since the interval contains 0, there might be no true difference. Kind of really helps. This is the harder one. And does that make sense right here? I am blank percent confident. I'm 95% confident that the true difference between the mean of UT students and the mean of Florida students is contained in the interval. Then we say here 9.87 to 10.13. Since the interval is completely positive, this is evidence that UT students is higher, have a higher, not GPA in this instance. This was like a test they took. We're going to take a real quick break right here. We're going to come back and do the t-test, and then we're going to do the chi-squared. So back here in just 1 second, you know what we'll do with the between bumpers video right here. A lot of people haven't seen that one. I'm getting my next cup of coffee. So hang out here. We'll be right back here in a moment. Be right back, everyone. Bye-bye. Hey everyone, we're back. Good to see you here. I think that we got some good stuff. Can you write out we have it? Good to see you here, Jenna. They're only positive numbers exactly. So let's take a look right here. We're gonna do the test now. So we are coming back, and thank you so much, Majed, right there, and everybody. Let's throw some more points out. And good to see you here, Jenna. We are going to do the 2-sample t-test now. The 2-sample t-test. 2-sample t-test. Solving a 2-sample t-test. Okay, so we're using the same information we've been doing this whole time right here. Can we just take a look at... Oh, thank you, Zachary. I appreciate that. That's got some coffee, just drinking mug right here. Good stuff, mister. Got my ring and my mug. I appreciate that. It's just some good practice. Sitting back, relaxing, grab your own coffee right here, and have a good time. Okay, so thank you, Cole, and everybody. Let's take a look right here. Now, what's interesting is that tests and confidence interval, thank you, Mary and John. Tests and confidence intervals are basically the same thing. Basically, Shanice, good to see you here. And so they're basically the same thing. We're not going to make a confidence interval now. We're going to say test to see if the difference is equal to 0. So the first thing, and we're going to do the steps right here, but if you notice, we already did it a moment ago. If you're watching or you've been following through with us here, we solved it like this. I'll explain how we did it so quickly in a moment, but let's do this step by step by step. Now, why is this called a 2-sample t-test again? Why is it called a 2-sample t-test right here? Why is it called a 2-sample t-test? And let's do this with the alternative that UT students have higher scores. Why is it called a 2-sample? There's 2-sample means, and we'll see that here in the formula here in a second. And what are we trying to investigate? We have 2-sample means, and our goal with this is to investigate not the sample difference, but we are making a hypothesis about the what difference. We are making a hypothesis not about the sample mean difference, but we are making a hypothesis of what the what difference might be. We are hypothesizing about what the what difference might be, the true difference. So we're going to look at the sample difference, but we're hypothesizing, is the true difference 0? Or maybe, and we could even write UT right here. So we can actually put in the names to make it a little more sense. UT is mean 1, Florida's mean 2. And we're asking, is the difference greater than 0? Now, the reason being that we're doing the difference greater than 0 is we're trying to see if UT is higher. Especially when it comes to jump output, you can look at this greater than sign right here. And with the greater than sign, you can just plug it between. So I do want to point out when you look at jump output, if you're wondering which way the alternatives go, you can take the output right here and you can see where it has the following. We would have here mu1, mu2, and then you can plug the sign of greater than right between, and that's the alternative for yes, greater than no. Does that make sense when you're looking at the output to be like, oh, this one right here is testing the true mean of yes is greater than the true mean of no. So that's one way, and that is this alternative right here when you're looking at the jump output. The jump output lists them in this order. It lists the does not equals alternative right here, the greater than alternative right there, and the less than, and once again, just plug it into the equation. So with the 2-sample t-test, we typically, you don't typically, good questions right there, MG. It just depends on the what. How do we know which alternative to pick? And MG, great question right there. How do we know which alternative to pick? Really good theory question. We know to pick the alternative based on the what? Based on the what? How do we know which alternative to pick? How would we know to pick this alternative? The researcher's question. It could be greater than, less than, not equal to. It's just whatever the question says. This question happens to be a greater than question to see if the difference is greater than 0. It says exactly, MG, great job. And this is the practice we want. Just be like, oh, the question will direct us to choose a certain alternative. So when it says with the alternative that UT students have higher scores, well, if UT students have higher scores, we'd see something like we saw in our data, 94 minus 84, which is greater than 0 because 10 is greater than 0. Now, we're not saying they have higher scores because of this, but just theoretically, we would see a positive difference right here. The way we're subtracting the means, if there really is a difference, that UT students have higher scores, we would expect to see in a sample a difference that is positive. So now we need to mark our what? Notation? Notation.
Notation, brother.
Let's mark that notation. Try to mark this notation with me because this is the key to solving the problem now. I think we have everything right there. Mark that notation. And so we go right here and we're just marking it. Y bar 1, which is the first mean, so that's just the first one you write, is 94. Y bar 2 is equal to 84. S sub, well, sure, why not? S sub 1, S sub 2 are both equal to 0.5 respectively. And then sample size 1, which is UT sample size, is 100. Sample size 2, which is Florida sample size, is 150. And that is going to be what we need. Well, we didn't mark the step this time. The first step right here was to write null and alternative. So write null / alt. So we did this right here. We wrote our null and alternative. We're going to fight the program right here. So we wrote our null and alternative. And take 2 seconds. What is step 2 now? I'm going to bring it back here in just a second. What is step 2? Step 2, now that we have our null and alternative, is to do what? Step 2, now that we have our null and alternative, is to do what? What is the second step now that we have our null and our alternative written out? So we got the null and alternative written. Now we do what? Step 2 is going to be solving for the t, the z, the chi-squared. Step 2 is to solve for the t, the z, the chi-squared. And that's where this is going to come into a lot of importance right here when we use the information given to us to solve it out. There we go. Perfect. It's a y bar right there. Okay, so now that we have our notation written, we're going to go to step 2 right here. And with step 2, we are saying we solve for the t, the z, or the chi-squared. Solve for test statistic. Test statistics are standardized differences, t, z, or chi-squared. And so with the t, the z, or the chi-squared, we need to know the equation, which is given to us on the formula sheet. The test stat, great job, Majed, right there. Excellent work. So the formula is y bar 1 minus y bar 2. You do subtract 0, but as the Rock would say,
it doesn't matter.
Subtracting 0 doesn't do anything to it. That's actually the hypothesized value right there. So we're seeing the difference from the hypothesized value. So the top is not only a difference right there, but it's a difference from the hypothesized value. So you could technically test other differences. We don't do that in our class, but nothing wrong with that. This is all going to equal to a t with degrees of freedom that are too complicated to find. Great job right there, Priya, solving it out right there. Priya, great job on the notations. Shanice, excellent points there. So now, s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. And this is equal to a difference of 94 minus 84. I'm off the screen, but I can be back over on here. So what do you notice I did? Did anyone remember when I solved this so quickly a moment ago and I was like, well, the answer is going to be this. Might still be in the calculator. I was like, oh, the answer is this if you watch it. How did I know this? Because what had we already found for the previous problem? What had we already found for the previous problem that then I was like, oh, the answer is going to be this? Basically, Zach, not correct the standard error. So we already found the standard error in the previous problem, and I know the difference is 10. So if you're watching the previous problem, we found the standard error. The standard error here on the bottom of it, we'll solve it again, but it's like 0.0645. Oh, no worries. They're literally tomato. It's just a naming convention. If you solve it out mathematically correctly, it's fine. It's very much virtually identical, just a naming convention. One comes from a sample, one comes from the population, and this is now the standard error. So that's the standard error. Double check your work, see you get the same numbers I do, but that is the standard error right there. And the top part of this is just a difference. So 94 minus 84 is 10. It's just how far are those numbers apart. And then the bottom right here is going to be 0645. We're going to carry out the decimals in the calculator for the remainder of this, but Priya's already done it. Another 100 points right there for 154.919. Now, when you look at this T statistic right here, this T statistic is ridiculous. This T statistic is absolutely insane. We would need to go to a T degrees of freedom calculator to figure out which T we are using. We already figured this out previously, but the degrees of freedom for this are a too complicated formula that we do not solve by hand. It takes the standard deviations and the sample sizes, and we figured out it's 212, and then we plugged that into the T-applet, which then shows us the shape of the distribution. 212 is basically normal, and now we plug in our T value of 154, and we do the greater than test. What do you notice about this? Who thinks they could have told me this p-value before even looking at the applet? You got a T statistic of 154. You're like, oh, the p-value is going to be this. Here it is, the p-value again. Could anyone have told me the p-value on the greater than test without going to the applet? Because remember, it's just the area greater than where you landed on the curve. The curve is like the normal curve right now and really only goes between 3 and -3. I mean, it goes further out. It goes to infinity technically, but most of the area, 99.7% on the normal curve, and this is basically a normal curve, is contained between 3 and -3. Large T values mean small P values. That's worth another 100 points right there. Large T values are more extreme and less likely by random chance, i.e. small P values. So we're saying right here, this difference of 10 points between UT and Florida students is impossible. Virtually impossible. So the whole point of solving for this T is to use the information from the T to solve for the what. The whole point of using this T information right here is to then solve for the what. The whole reason we solve for a T statistic is to now get a what. The whole reason we solve for a T statistic is to get a what. It's just not going to happen. The whole reason we solve for a T statistic is to get a p-value. So the step we need to do now, step 3, is going to be solve for the p-value. Now, I did it a little bit quickly because that is something you would probably see in jump output. So let's do a jump output relevant p-value question right here. So I'm going to do a kind of jump relevant p-value question. So let's do a solving for a p-value with jump output. See if you can solve it. Give me a half second right here. I need to find one if I have one open that could be used. Okay, give me a second. I'm going to do a solve for a p-value from a 2-sample T, which is more relevant to what you would be doing. And of course, they're all turning out very, very tiny, which isn't good for examples. So I'm going to do where you'd actually have to solve for it. Cool. Got one. Okay. This is more test relevant as soon as I make this appear. And give me a second. I'm going to blank out some numbers right here. And then we're going to solve for some p-values that are more test relevant. Okay. Here you go. Can you find the missing p-values? We have a p-value missing here for the does not equals test, and we have a p-value missing here for the less than test. Now we have the second p-value for the greater than test. So what do you know about these? So solve for the p-value, which this is more how we would do it on the test. So a little more test relevant right here. So this is not our problem anymore. I think Leo has found one. Which one did you find, Leo? The first, the second, or the third? The second one's given to us here. So great job, Leo. And how did you find that, Leo? Leo is super quick right there for 100 points. How did you find this p-value right here? So that these two p-values must sum to 1. Because what you're doing is you're going above the value for the second one, and the other p-value, the third one, is the below. So you're going above a value and below a value, so those have to sum up to 1. So those p-values right there have to sum to 1. So good job, Leo. That is the one I would solve for first. Now that you've solved for that one, how could you solve for the other one? So now that you've solved for that p-value right there, which is the smaller of the two p-values, what could you do for the other one? So now we're just missing one more p-value here. A little more test relevant on this right now. But what could you do to solve for the other p-value? How do we solve for that does not equals p-value? And the does not equals p-value is going to be, you're going to take where you landed, and you landed at a t-score of -3. You can see it right here. Here's where you landed. And then you're going to reflect it on the other side. So you're going to reflect it. So it's going to be the reflection. So what do you notice mathematically you're doing? So this is the p-value right here for the first one. We'll put like a 1 right there. It's the reflection of the other side of the smaller. So mathematically, it's the reflection on the other side of the smaller of the two. The reflection on the other side of the smaller of the two. So what should it be mathematically? It's not going to be 1. Good guess right there. So think about this. It's the reflection of the smaller. It's the reflection of the smaller. The does not equals is always double the smallest. So what's the smallest p-value? 0.00008. What's double the smallest? Great job there, Priya. You've solved it. There it is right there. It's double the smallest. Does that make sense? Just more practice with this. And I do want to point out that the t-statistic right here, who can calculate the t-statistic? Last thing, I always like showing this in this output. Who can calculate the t-statistic? Because this is the difference. Like, everything I'm highlighting is the same right there. And then this is the standard error. I should have blanked it out too. And then that is the t-statistic. And then how do you solve for that? How do you solve for that? Because that equation on the left is the difference in blue. That's the difference between the two sample means. Sample mean male minus sample mean female. And Zach's got it right there. It's the difference divided by the standard error. So you just divide the numbers. -0.40 divided by 0.13 is this right here. So you would just divide these two numbers literally and get that literally. I mean, yeah, that does apply. A lot of times people say literally and they don't mean it. Like, literally divide these numbers and you will obtain it. So a little bit better about what we have right here. And there's the t-statistic right there. The interval is also given to us right here, and the interval does not contain 0, so we do think there is a difference, which we do have evidence of that via this. For our problem, just to finish off our problem, we found this t-statistic of 154, which is a p-value of 0. So now we need to ask, do we reject or fail to reject the null? Let's say we use an alpha level of 0.10. So this should be pretty easy right here. Do you reject the null or fail to reject the null? Do you reject the null or fail to reject the null right here? This is step 4 we're on right now. So this was step 3 to find p-value. Step 4 is reject or fail to reject. We definitely reject the null. So take a moment and try to write out the full sentence right here. So here we'll put on the screen right here. We found a p-value of Leo, this one's even crazier. It's very, and the null hypothesis here, I'll write these out right here. We found a p-value of basically that we're saying an alpha level, alpha equals 0.10. And so take a moment and go down the pathway here. I'll write the null hypothesis right here while you try to write out the finality of our test. Yeah, it's ridiculously significant. This is a huge difference in scores on the test. So the null hypothesis for this was that for UT and Florida, there is no true difference between the score on the test, that they're equal. That UT and Florida have no difference between their test scores. The null is that UT and Florida have no difference between their test scores. Well, you can do it that way. That is accurate. What do we have right here? Then we got chi-squared, and then we finish for the day. So what would you say? Our p-value is basically 0. So what are you going to say? Give it a shot. Good practice. Thank you, Vijay. Watch what we say. I reject the null hypothesis that there's no true difference in test scores between UT and Florida at the alpha level 0.10 with a p-value of 0. Priya, you got it. And then finish it off right there. You got it. This means I what? This means, so then you got it. Just go path 1. You're going down path 1. And then make sure you remember we are testing to see if it's greater than. So, and just think of how you would communicate. This means I do have evidence. I might finish it off right here. This means I do have evidence for my alternative that UT students have a higher test score than Florida students. Yay! Does that make sense? This means I do have evidence for my alternative that UT students have a higher test score than Florida students. So we have a strong evidence for that. That's got it. That's testing 2 means. And we did a one-sided test for 2 means. I reject the null hypothesis that there's no difference between the test scores of UT and Florida students. Sprinkle that in there, Zach. At the 0.10 alpha level, the p-value 0. This means I do have evidence for my alternative that UT students have it. Yes, Zach. 1,000 points, Zach, especially at the end right there. Hey, what's up, Kristen? Good to see you here. We're throwing 1,000 points, Zach. That's great, especially at the end when you clarify. Ubot saying, hey to everybody. I reject the null hypothesis that there's no true difference in the test scores at the 0.05 alpha level with a p-value. And this one technically gave a different alpha level, Majed, but don't worry. Technically gave a different alpha level. This means I do have evidence for my alternative that UT students have a higher test score than Florida students. Good work right there, Majed. Oh, you said, yeah, that's what I thought for you. You're probably doing. Excellent work, everybody. We're doing the chi-squared test of independence. Last bit of notation. Let's go check it out. It's our last test of the day. Let's go over to the formula sheet and do the chi-squared. So formula sheet, chi-squared test. And so we're going to start by talking over the formula sheet. And then after we do the formula sheet, we will then do a problem with it. What is the formula sheet? Formula sheet, here it is. Chi-squared test of independence. I know you can't see it yet. This is an easier one. It's a little bit easier of a chapter. Okay. That's so awesome, Majed. That's really great. Great job. Does small p-value mean unlikely by random chance and statistically significant? That's what it means, Priya. Small p-values mean unlikely by random chance, and the definition of statistically significant is p-value less than alpha, which is small p-value. So small p-values imply statistical significance. Like when the p-value is smaller, it's more likely to be statistically significant. Statistically significant means unlikely by random chance, i.e. small p-value. So does that make sense? 100% what you're saying is accurate right there. Also means reject the null hypothesis due to statistically significant results that were unlikely by random chance. So it's a lot of redundant language in the concepts and ideas. Priya, great job, and keep asking those questions. Small p-value means unlikely by random chance. We can't say it's not by random chance. We say unlikely because remember, it's a probability. So the smaller the p-value, the less likely by random chance your results are. It could be by random chance, but it's unlikely, i.e. the p-value is the probability. Okay, let's head over here and do the chi-squared. Okay, we're here on the formula sheet doing the chi-squared formulas. Cool. So let's see what we have. We need to know what the observed are. We need to know what the expected are. And then we need to know what the cell chi-squareds are. So these are cell chi-squareds that we find right there, and degrees of freedom. There's not nearly as much to know on this. So observed are going to be what? If you talk about something you observe, it's how many individuals you see in each group. So the observed equals how many individuals you see in each group. Now, I think what's tough about this one, you bet it's chi-squared time, is probably it's going to be easier to do this if we have a little bit of jump output. So we're going to go over here and grab some jump output and get the chi-square data right here for ourselves. Okay. So let's take this table right here and use it to get values. Now, important things we should know is that the chi-squared test of independence is 2 categorical variables, and we are going to use the mosaic plot and the contingency table to visualize this and see the counts of the observations. So we're asking whether or not you're born in Tennessee, TN, is associated with you being in Greek life. So when you look at this right here, these are the counts. So can anyone tell me, how many people do you observe? And great job, Priya, right there. How many people do you observe being born in Tennessee and being in Greek life? Answer this question. We observe blank people born in Tennessee and in Greek life. 165, great job right there. You could have, yes, jump output definitely could be on there. And we've done a little bit today. I think we did more yesterday. Yeah, we did all the jump output stuff yesterday. Check out yesterday's video, a lot on jump output. Today is the formula sheet. Basically another way to learn through it. And great job right there, Zachary and MG, all the great questions. Keep it up. And we observe 165. So notice that the observed are actually called the what down here. The observed are called the what. In jump output, observed are called what? In jump output, observed are called counts. So they're called, or it's just called count, right? And think, it's the count data. So that's how many you count in each group. So that is the count data right there. So we have the count of the observations. Next, we go right here and we go to expected. And I always like to do this example for expected because just think about this. Let's say I tell you that turns out 20% of my former students are celebrities. Like I'm talking Tom Cruise. You didn't know it, but he took stat 1 here. You got, who else? Michael Jordan, Michael B. Jordan too. All the Michael Jordans have taken my class. So 20% of Brian's former students are celebrities. So let's say celebrity right here. Does that make sense? 20% of Brian's former students are celebrities. And I've only taught 1,000 students, contrary to popular belief. So we have the 20% celebrity right there. So we're going to say celebrity no and celebrity yes. Does that, who's following me on this example? 20% of Brian's former students are celebrities. Does that make sense? We have 1,000 students total. And we have right here that 20% of them are celebrities. And you can just see it right there. Now we're going to throw a party, big party. And we're talking big party here. Many people just want to show up as they can. We have, did you show up to the party? And we put right here, yes. And we put here, no. Now, 500 people showed up to the party, which means how many people did not show up to the party? Just tell me if 500 people showed up out of the 1,000 former students, how many people did not show up to the party? If 500 people showed up, then logically, out of the 1,000 former students, how many did not show up? Also 500, right? What percent of Brian's students showed up to the party? Just to answer this question, what percent of Brian's students showed up to the party? What percent of Brian's students did you see show up to the party? What percent? You saw what? 50%, right? Now, I haven't told you these numbers. If I tell you these numbers, I will be telling you the amount we what. If I tell you the numbers in here, I will be telling you the amount we what. If I tell you those numbers, like if I say the number here is this, the number here is this, I'm telling you what I what at the party. Well, we're going to solve that here in a moment. If I tell you the actual amount, that would be what we observe, right? So if I tell you, oh, there were like 20 celebrities showed up, that's what we observe, right? But we're going to solve right now what we expect. And what we expect is based on the distributions of the amount that showed up and the amount of celebrity, right? Pretty much, Mary, yep. I think a lot of classes, especially math 123, does a lot of game theory stuff. So observed is how many we actually see at the party because we observe them. And expect is like, well, what would I expect? So I don't want you to solve the formula. So don't do this by solving the formula. I want you to think through it logically. How many celebrities do you expect to show up to the party? Before knowing this information, how many celebrities do you expect? And then let's look at how it's found mathematically here. Just think through this. Half of Brian's students showed up. 200 are celebrities, 20%. So wait, do you expect 5? And Jed, good work there. Don't worry. So Priya says they expect 300 to show up. 300 celebrities. 300? Well, we have a problem with the table right now. The table's not going to add up. Because, wait, just tell me this. How many celebrities are there? Just tell me how many celebrities are there. Just follow this question right here. How many celebrities are there? Just tell me how many celebrities there are. Look at the data table and tell me there's this many celebrities. 200. We're all celebrities. There's 200 celebrities out of the 1,000 students. Does that make sense? There's 200 celebrities, and we're just looking at this right here. This is just, there are 200 celebrities out of the total 1,000. Does that make sense? There's 200 celebrities out of the total 1,000 students. The people who showed up to the party, half of the students showed up. So think of this. If half of my students showed up, 200 celebrities, you'd expect what of the celebrities to show up? Does anyone see the logic here? If there's 200 celebrities and half the students showed up, Kristen's seeing it, well, I'd expect half of the celebrities to show up, right? Now, we're not saying they're more or less like, we're just saying, oh, well, if half of Brian's students showed up, I'd expect half of the celebrities to show up. Does that make sense? Because that's half of the celebrities. And I expect half of them to not show up. Does everyone follow the logic right there? Who sees the logic on that? I'm going to change the numbers here and make it a little more difficult, but tell me if you don't get the logic. And then we're going to do it mathematically where we'll solve it out. Well, this right here is half of the celebrities showing up. Does that make sense? This is what we expect. Now, we're not saying what we observe, and Kristen's got the math right there. What about if I said to you only 10% of Brian's students showed up to the party, which is still great, still great. Only 10% of Brian's students showed up. What percent of celebrities would you expect to show up now? Just tell me, if 10% of Brian's students showed up, what percent of celebrities would you expect to be there? Don't solve the full thing yet. If 10% of Brian's students showed up, you'd expect what percent of Brian's celebrities to show up? 10%. So how many celebrities would you expect to show up now? We're talking Tom Cruise. We're all celebrities here, but we're talking some Tom Cruise and some Michael Jordan, Michael B. Jordan there. Saying, I'm going to this party now. So if you'd expect 20, right? Does that make sense? That's great work right there, Dem. And so let's see the mathematics for this, which is given to you on the formula sheet. We've just been working this out right here. I like to write it the following way. That's the formula we've been working this whole time, but we've been trying to understand the theory of it. What we're doing is row total times column total, and it's written up there, over grand total. The N right there is the grand total. So what you need to do is you need to take the row total times the column total over the grand total. Now, this is not how many you observe, it's how many you expect. And so what we do right here is we circle the numbers, and then we multiply them, and we divide by the grand total. So take a moment right here and tell me, does this make sense how to do it mathematically? This is equal to the expected count. So in the below problem, you would get 20 right there. 100 times 200 over 1,000 is 20. So now thinking about this right here, what would happen if you tried to solve out? We have it down here, right? What is the expected cell count for this one right here? What is the expected cell count? So take a moment and solve for the expected. So remember, do the trick. Do the trick. See if you can solve the expected cell count. Need to find its row total over column total over grand total for the expected. How do you know which of the rows and columns to use? Good question right here. We zero in on it. You go like, there's the row, there's the column. So you kind of do a like bullseye on it. Does that make sense, Majed, right there? 174. That sounds about right, Priya. We'll find out here. And so those are the rows. So you just do like a crosshair on it. So you just go the column, go down it, and the row, go across it. Nice work, Majed. And thank you, Majed. Keep up those questions. That's how we know the rows and the columns to use. Just crosshair in on it. Be like, and then circle the numbers. When we did written tests, I would always be like, please draw this out. Please draw this out. We don't have the ability to like do it, but I would be like, just take your test and write the formula on it like that. So I would print off tests a lot of times, and I would print off like questions. I'd be like, draw it to find it, because you're just solving the equation here of row total times column total over grand total. And that's going to be what we expect for that cell. Great work. A lot of people solving it right there. So once again, do the crosshair technique on it. I think I didn't hit the wrong button. Find out. There it is right there. And we can confirm via the jump output. That's not the one we're looking for. Not the output we're looking. Not the output either. Where is it? Right here. Jump output will confirm, so you can always do practice problems where you can find it. So now that we have this, we're going to update our table a little bit here, because now we're going to try to find a cell chi-squared. So that is how we find expecteds, and really good practice right there in theory on it. Now, what are cell chi-squareds? So this is a cell chi-squared value. These are how far the observed is from the expected in a standardized version. What do we mean by this? Well, when we look at this, we could just take the what between the observed and the expected. We could just take their difference, right? How far away are these numbers away from these number? Like, how far away is 165 away from 174? Just round it for me. Just tell me if we subtract 165 minus 174. Be careful. If we subtract those, we'll get what? If we subtract those, we'll get 9 and technically negative 9. Does that make sense? So we'd get negative 9 here, rounded. We'd get positive 9 here, rounded. And over here, we would get negative 9. And here we get... What happens if I add together all these numbers? What happens if I add together all these numbers now? And I want you to see something between them. This one and this one. This one and this one. They sum to 0. They sum to 0. That's a problem. That they'll always sum to 0. So what do we do when we solve the cell chi-squared? So a chi-squared of a cell, which is the next thing on the formula sheet, is equal to the observed minus expected, but we don't just do observed minus expected, we do what to that difference? So what do we do to the difference so it's no longer negative? It can't be negative if we do this. Mathematically, by doing this, you'll never get negative. Exactly. So we square the difference. So all those would be positive here. But now, since we've kind of increased it so much, we want to standardize it by something, and we standardize it by the expected value. So it's observed minus expected squared over expected. The expected gives it like a standardization. We talked about this theory a lot in class, because if I tell you that house went up $1, what would you say to me? Or if I say that house cost $10 more, we'll use $10. The house went up by $10. What would you say? You looked at the house and this year it's $10 more. Would you say to me, what? I say the house went up by $10. You'd say to me, what? Doesn't matter.
It doesn't matter!
But what if I told you the price of a cup of coffee went up by $10? You would tell me that really does matter, because you're using the expected value. If you expect to pay $200,000 for a house, or $400,000, they're going through the roof. Then $10 is not that big of a difference when you standardize by what you expect. But if you do it for a cup of coffee, you don't expect to pay that much for a cup of coffee. So now it's going to be a much larger difference. Does that make sense? Why we use the expected to give context to a difference of $10. A difference of $10 for a house is like, who cares? A difference of $10 for a cup of coffee is like, what in the world is going on? And we're just using the expected to give us context to this difference right here. That's why we do this mathematically. So beyond knowing the theory for this, we should know where to grab these values. So we need to know that the expected is the value right here. We'll do it for the same cell we've been solving for. And the observed is the count once again. So who here can solve for this cell chi-squared value? Who's got this cell chi-squared value right here? That cell chi-squared value is what? I think we solved for this one yesterday too. So we need to plug in our numbers. Observed minus expected squared over expected. It's like 0.47, I think. I think we did this one yesterday. 0.47 about. Who's got it for us right here? We just love solving for that cell right there. So observed 165. 0.47. Yep. I remember that one from yesterday. I was like, wait, we did this one, right? I like numbers. I like turtles. So there it is right there, and that is equal to 0. There we go. So what's the point of finding cell chi-squared? So we're doing the formula sheet right here. Why do we find the cell chi-squareds? You've even got hints for the test right here. Why do we find the cell chi-squareds? Why do we find the cell chi-squareds? Why do we find the cell chi-squareds? Because eventually we're going to do what with all the cell chi-squareds? We just found one of them. We could go back to our output and find all of them. So why do we find these cell chi-squareds? We're just going to show only the cell chi-squareds here currently. Why do we find those cell chi-squareds? We sum them up. And who can do it in their head? We do this in our head here so quickly. Who can add up 0.3964, 0.2597, 0.7130, 0.4670? Can you do it before me? Can you do it in your head? Who can do all these numbers added up? Who can do it? I'm doing it here. It's not too crazy, but who can do it? Leo, how did you do that, Leo? How'd you know that? Did you do it on your calculator? Or wait a minute, did you look down there, Leo? Did you know that the sum of all the cell chi-squareds? Oh, I think Priya actually did it with me too. The sum of all the cell chi-squareds is the Pearson chi-squared test statistic. So the sum of all the cell chi-squareds, these values right here that we've been finding for by doing the observed minus expected squared over expected for all the cells, is the Pearson chi-squared test statistic. Now we have to take the Pearson chi-squared test statistic and go over to a chi-squared applet. But when we go to the chi-squared applet, we must know the what for the chi-squared we're doing, which is in this output. Anytime you're saying I'm going to use the t or the chi-squared, you always have to know the what for the chi-squared or the t. Now we're talking chi-squared here, but you do have to know it for both of these. Anytime you do the t or the chi-squared, you have to know the degrees of freedom. Great job, Majed, right there. And so we go over here, and how would we possibly know the degrees of freedom? So let me look at this. Brian, that's a what by what. Brian, that's a what by what. Start by telling me it's a what by what to begin with. And I'll even try to make it tricky down here. Brian, that's a what by what. Brian, that's a 2 by 2. Subtract 1 off each, 1 times 1. Now be careful. A very common error, we always like to point out this error, is when people get tables like this, they might say it's a 3 by 3. This is not, great job everyone right there. This is not a 3 by 3 because you only count the groups. 1, 2, don't count the totals. Totals are not groups right there. The totals are not something we count. So we only count that there's 2 groups here, there's 2 groups here. And so that's a 2 by 2. The mosaic plot also lets us see it's a 2 by 2. Don't include the totals, Jinx, right there. So we don't include the totals. 2 by 2 reduced by 1, 1 times 1. Just for practice, because I think these are nice and easy problems. Solve this one out right here. How many degrees of freedom? Be careful. This is a more complex one we did yesterday. Oh, chat is so crazy. You might have been first on your screen for both of you because there's a delay when you enter something that the other people said it. The other people see it like there's like a 3-second delay by what you do and what you post because Google kind of does a little checking on stuff. So you both might see it first on your screen. No, you both might have. You said degrees of freedom are 16. I've stopped doing like who answers first in the chat and then rewarding people because every time I would do that, people would be like, I answered first, or I'll send you a screenshot of it. I answered first. But because you see it right when you send it, everyone else might see it like a half a second to a second later. I don't know how long it takes sometimes, but it's so interesting because I used to do that, and I had people being like, "No, I answered first," because I was giving out like actual prizes and stuff or like points. They're like, "No, I answered first, I swear." And so I would like show the screenshot on my screen. Oh, they encrypt them too. That's interesting, Leo. Leo, you have so much good knowledge. Everyone here has tons of great knowledge, but Leo, that's really cool. I didn't know that. And this is a 5x5 reduced by 1, and people did a great job. There are 16 degrees of freedom right there. Do we have another one to quickly show? Here we go. Oh, where'd that go? Degrees of freedom on this one. If you know degrees of freedom, these are quick and easy problems. Yeah, it is weird. Degrees of freedom on this one. If you know it, it's super quick. If you know how to get degrees of freedom with chi-squared ULI, say, oh, boom. 2x5, and then go down here, 1 times 4. And that's how we're doing it. Just remember, say it's a 2x5, 1, 2, 3, 4, 5, 2x5, and 1 times 4. No worries, Majed. Here, we'll do one more Majed for you right here. Don't worry, this is practice. Hey, this is where we get it wrong, so we can get it right on the test. So we're going to do another one right here. Trying to make it a little more complicated. So this is a more complicated one, harder one to get. Now we're going to do it in steps. Follow me the steps here. No one said the degrees of freedom yet. You ready? First, start off by saying, Brian, that's a what by what? Brian, that's a what by what? Brian, that's a what by what? Start by saying, Brian, that's a what by what? Brian, careful right there. It's a 5x4. Does that make sense? 1, 2, 3, 4, 5. 1, 2, 3, 4. Does that make sense? Brian, it's a 5x4. No worries. And now what do we do? It's a 5x4. Now what do we do? It's a 5x4. Leo's showing us we drop and we get 4 times 3. Does that make sense? Majed, you did it. That's right. It's going to be 12 degrees of freedom. You just solved it. Great practice. And that's what we like to see right there. Lots of good practice and good work. John right there. Just making sure we can get those pretty quickly and we know how to solve it. It is given to you on the formula sheet where it says rows -1 times columns -1. And just knowing how to solve it really quickly is easy. Once again, the degrees of freedom for our problem right here is what? Just look at it. Brian, that's a what by what. Be careful. Make sure you look at it carefully. The degrees of freedom for this one are what? You can just straight solve the degrees of freedom on this one. There's a mistake that can happen while doing this. Great. And Majed, you're getting it. And damn great work there too. People are saying, Brian, that's a 2x2. Once again, don't include the totals. Once again, we're just talking about when we say 2x2, we're talking about 2x2 is right here. There's 2 answers here. There's 2 answers here. That's when we're saying it's a 2x2. There's 1 degree of freedom. Same thing for, we actually pulled up jump output for this. This is also a 2x2. Don't use the totals. That's a 2x2. Don't use the totals. That's just the most common error I see when doing this. So the reason we need those degrees of freedom is we have to put them into the applet. When we put the degrees of freedom into the applet, it controls the shape of the chi-squared. There's the shape of the chi-squared we are using. We then use the chi-squared Pearson test statistic and enter that in, the 1.836, into the applet. Jump will do it for us too. We go over here to 1.836. Now, you always do a greater than test because we're seeing something more extreme than the differences we saw. The chi-squared is a one-sided greater than test to look for differences more extreme than the differences we saw. So it's just differences more extreme because it's all positive differences. And it starts at 0. The chi-squared can't have negative differences. And so, yeah, this right here, what would you say? Now, let's look. We got a p-value here. So we basically ran the test. So let's go look and think about this. Now, be careful. What is the null hypothesis for this test? So let's put a quick note right here. Interpreting chi-squared test results. So interpreting chi-squared test results. What is the null hypothesis? Suppo said, independent. Greek life and born in Tennessee are independent of each other. That means if you know someone was born in Tennessee, that would tell you nothing about them being in Greek life. The null hypothesis is that the two are independent. And the alternative, so that's the null, is that they're not independent. So that's the alternative, the HA. And so the alternative is this full thing right here, where the null hypothesis is that they're independent. Greek life is in it. Great job, Majed, right there. I like that. The Greek being in Greek life is independent of being born in Tennessee. The alternative being that Greek life is not independent of being born in Tennessee. Like maybe if you're born in Tennessee, you're more likely to be in Greek life. I mean, that could be possible. Maybe you're like, hey, Tennessee, Greek life. I don't know. Possible. So we're going to look to see if there's evidence of this, and let's go look. We had a p-value on our test, and we should be looking at, can anyone tell me the p-value? What is the p-value? Important we know this. We'll grab it. What is the p-value? I think there's test questions that literally ask this. I've been looking over the toast. What? Oh, we got 0.754. Yep, basically 0.7. And then I would carry every decimal it shows. If it shows those decimals, I'd put in all those decimals. Great work right there. 0.716 according to the applet. Correct, Majed, right there. And basically, and if you do enter in something like 0.76, you wouldn't want to use this one here. The likelihood can be different. It's a different way of doing the test. We don't do it that way here. So Majed, according to the applet, that is correct. And then this jump does a little more decimal calculation. Why are they different? Basically, different statisticians came up different ways of testing. The likelihood ratio is not something I use, and I should read more about it. I just haven't used it in so long. I can't tell you enough details on it. But Priya, great question. Two statisticians had two different ideas and came up with two ways of doing it. Also, just really, really quickly on that, another statistician, Ronald Fisher, has the Fisher exact test, and look at how this has a different test right here, and you can actually do the sidedness on this. So the Fisher exact test, which is used for matrices of same size, a 2x2, a 3x3, a 4x4, can do the Fisher exact test. Ronald Fisher right there, the one who would not let William Gossett of Guinness Beer publish his work until William Gossett came up with student tea distribution. So that is Fisher right there, the guy who didn't like William Gossett. Fun stats history for us all. So now that we have this, we have our p-value, we have our null hypothesis, our alternative, we have step 2. So this up here was step 1. We're literally doing the test. Step 1 was write our null and alternative. Step 2 was to find the Pearson chi-squared test statistic. And then step 3 is to find the p-value. And then step 4 is to do what? Step 4 is to do what? What do we need to do here on step 4 now that we wrote our null and alternative? We have our Pearson chi-squared test statistic, which was the sum of all the cell chi-squareds. Then we found our p-value. JMP's usually going to give us that. So there's the p-value. And then step 4 is to do what? We'll say alpha usual of, well, let's not give it. Hint, hint, hint. We need to and choose to, oh, there we go, Priya. Great work. We're going to reject or fail to reject. Let's grab our wording right here that we have on one of our slides already. And we're going to talk about, do we reject or fail to reject the null hypothesis? And we're just going to drag and drop. There it is right there. Go down one more. There we go. So we need to see if we reject or fail to reject the null hypothesis. So what do you choose to do right here? Do you reject? We're not going to state an alpha level. So what should we assume? Conclusion, great job. Our conclusion, yes. Are you following along from our class or another class? Good to see you here, Curio. Our conclusion, correct. So we need to reject or fail to reject is the last thing. We need to state our conclusion. Excellent work and get 100 points right there. Thank you for being here. We need to reject or fail to reject the null hypothesis. So think about this. When do we reject the null hypothesis? Reject the null when the p-value is what? Reject the null when the p-value is what? Reject the null when the p-value is what? P-value is low. Reject the null when the p-value is lower than alpha. So in this instance right here, our p-value is this. We assume alpha of 0.05 unless otherwise stated. So we can do an assumption on alpha. Our assumed alpha, because the problem never said it anywhere, is going to be assumed to be 0.05 unless otherwise stated. And it's not stated, so we're just going to assume it's 0.05. So try writing this sentence out right here. Take a moment. Try to write out this sentence. Remember, this is the practice we need. This is our first time doing it. Like this time we went this way on this problem. Remember, the null hypothesis is what we need when we state the null. So there's the null hypothesis right there. The null is that they're independent. Greek life and being born in Tennessee is independent of each other. Alternative is that they're not independent. So try writing it out down here for your conclusion. I love it when we get random people here. First random person was Calzone Tyrone from New York. Came in like 3rd place in one of our first Kahoots. Shouts to Calzone Tyrone up in New York. Who else have we had before? Got a lot of great visitors. So we're always welcoming to, if you want to swing by and ask questions and learn some stats. and drink some coffee. We're just waiting for, this is the last question of the day, I think. Another 3-hour stream tomorrow. We'll do a little review tomorrow, and then we'll do the Kahoot. So tomorrow might be more focused on here. I failed to reject the null hypothesis that Greek life is independent of being born in Tennessee at the 0.05 alpha level with a p-value of 0.754. This means, oh, that's awesome, Curio. What do you do? What do you do? You love some stats? That's awesome. This means I do. Majed, wait. Majed, you're right there. Yep, Alyssa's SI review sessions are tomorrow. You're right there, Majed. Now remember, if you fail to reject the null, what do you have for the alternative? If you fail to reject the null, you're right there. You're gonna have a few more answers right here. If you fail to reject the null, so I failed to reject the null. I didn't reject it. So if you do not reject the null, which is another way of saying it, we use the classical words, but you could say I failed to go to the mall today, so I did not go to the mall. The Greek life is independent. I think so. Let me read Priya's. I failed to reject that being born in Tennessee is independent of someone being in Greek life with a p-value of 0.754 at an alpha level. At the alpha level, so we'd say like at the alpha level of 0.05. This means I do not have evidence that Greek life is not independent. So for the last part right there, Priya, this means I do not have evidence that they are not independent. So state the alternative there. Does that make sense? So here, I'll read through it slowly. Let me see. I think we had another answer. Kristen said, we fail to reject the null that Greek life is independent of being born in Tennessee at the 0.05 alpha level with a p-value of 0.754. And then, as Curio said right there is not enough evidence to reject our null hypothesis. There's not enough evidence for the alternative. Great work there, Curio, and that's excellent advice. That is great wording for your sentence right there. I fail to reject the null hypothesis that Greek life is independent of being born in Tennessee at the 0.05 alpha level with a p-value of 0.754. This means I do not have evidence for my alternative that Greek life is not independent of being born in Tennessee. Majed, 1,000 points and great practice. Remember to just state your alternative. We're always giving that context right here, Curio. Greek life is in great work, Priya, on the very end. Remember, the alternative is that they are not independent of each other. And just think about this right here. I love to kind of talk about the test and stuff. We hope to see data like this on the test. Let's say people who made an A. Let's go here for grade on the test. And let's go here to A, not A. A, not A. Let's say attended reviews. And you notice, what kind of variables do I have right here? What do you notice about my two variables? They're both what? Oh, no worries, Mary. What do you notice about my two variables, which means we're doing this chapter? What do you notice about my two variables right here? They are both categorical variables. We got some cats in the chat. We need like, if you say cat, we should do that. We should put cat emojis. So is that the cat emoji right there? I'll fix that here in a second. But we should have Mubot do some cats, I think. Let's go here to 820. I'd love it if the data works this way. Oh, nice. And then attended. Oh, didn't do the same right there. Cool. And give me a second. We're gonna put Mubot doing the cats real quick, and then we're gonna do the rest of this problem. Commands, Mubot, cat, response. There we go. Here we go. Wait, he doesn't like that one. He doesn't like MG. He doesn't want to do that one, I think. No. Well, darn it. Okay. Okay, now if you type cat in the... I should have taken that one. All right, 2 seconds, Mary, and then we'll do the rest of this problem. I really like that cat emoji right there. And Mubot is... Here, we'll do that one. I always like it, the fun things where Mubot responds. Okay, let me fix this. All right, and then we're going to get serious. Okay, there we go. Oh, and I just have it as the just the word cat right there. So, yeah. Okay, so we got two categorical variables right there, two categorical variables right here, and so everyone's testing out the new commands right there. Always getting Mubot to respond to us. And with this, two categorical variables are going to be everyone loves the new command. A mosaic plot and a contingency table. So the way I like to read this in Jump, does attending reviews what your grade? Think about this just the way it's described right here. Does attending reviews what your grade? What words would you put this? Does attending reviews what your grade? Well, improve we could say, or think of the name of the variable. Does attending reviews what your grade? Does attending reviews, think of the X. I know, right? That's what I like. I like that, MG. Does your attending reviews explain your grade? Does that make sense to put it in the X variable? Does attending reviews explain your grade? Which is the same. Everyone's doing some synonymous words right here. Great work, 100 points in the chat. Is there a relationship? Does it affect your grade? Does it increase your grade? Does it explain your grade, making it the X variable? You want to know why you get certain grades. So that's why this is the Y variable of interest. Like, why did I get that grade? Maybe attending reviews explains why I have a certain grade. So the Y is the question. Why do I get a grade? X is what explains why something might happen. We need to put in here the count, and let's go right here, the frequency for the count. Whoa, what do you notice right here? 2 seconds, I'm gonna make this all purty. What do you notice right here about this output? What do you notice about this output? Just think about which group you'd rather be in. Here's the students who attended reviews. 87% of them made A's. Here's the students who did not attend reviews. 26% made A's. What do you notice about this output right here? What do you notice about it? And what's interesting is almost half the students made A's. That's 53%. It's actually right off the screen. Will it show up right here? There it is. 53% of students made A's. Not quite an MG. 100 points. Not quite correlation. There looks to be an association. Correlation is only between two quantitative variables. So correlation is only between two quantitative variables. QQ, straight enough, no outliers, plot doesn't thicken. So we would say there looks to be an association. And check out Alyssa's SI reviews right here. Now think about this. What is the null hypothesis for this? And great job, MG, with that correction. What is the null hypothesis? Just tell me like I'm your friend. Like, be like, hey, Brian, our null hypothesis here is that attending the reviews and your grade are what of each other? So your null hypothesis would be what? We're just doing another like mini question to end off right here. Attending reviews and your grade in the class are what of each other? And think about what that means as you say it. Attending reviews and your grade in the class are what of each other? I like that right there. Priya said the grade you make is independent of attending reviews. And that kind of means, as The Rock always tells us,
It doesn't matter.
doesn't matter. Do you think it matters here? Yes or no in the chat. Do you think it matters according to the data if you attend the reviews? Do you think it matters according to this data? Do you think it matters if you attend the reviews? Would you say yes, it matters, or no, it doesn't matter? It does matter. Rock can't say that anymore. We'll put it back on the soundboard in a little bit. It looks to me like it does matter. So what logically do you think we should do to the null hypothesis? Good to see your Kendall. What do you think we should do logically to the null hypothesis? So now that we are saying it looks like it does matter, like if you attend the reviews, like it looks like you're more likely to make an A. The null hypothesis is that they're independent of each other. So since you said reject, take a guess at what the p-value will be down here. So we think it looks like they're not independent of each other. So the p-value is going to be super duper duper low. P-value is very small, very, very small, basically 0. We reject the null hypothesis. Exactly, very low p-value right here. So super low p-value, I reject the null hypothesis. There's evidence that attending the reviews is not independent of your grade. That means they're associated. Not independent means, you could say dependent if you'd like. So exactly, small p-value. But think about this. The difference is now, we'll go ahead and do this right here. The difference is now, if I start doing this, oh, I didn't click the button. Redo, what am I? There we go. The differences now look to be a lot wider. We'll actually do a little bit of a difference. So now look, the people who attended the reviews, a little bit more of them made an A. Does that make sense? Does everyone see here if you attended the reviews, a little bit more of them made an A? Little bit more. Does that make sense? The people who attended the reviews, 29% made an A. The people who did not attend the reviews, 26%. So that's a difference of 3%. This is awesome. Oh, Shifted. I used to do stuff like that. Shifted Stokely. That's cool. You're welcome. Majed, glad you got to relax. So the differences here look very small. So now it looks like, so we don't know if they're independent. MG, great answers right there. They look more independent. Wouldn't you agree that now they look more independent, that whether or not you attend the review, your grade is not really associated with that. It looks more independent. Does that, MG, you're totally right. Not that it is independent, but it looks more independent. Does that make sense to say it looks more independent? The way it would look most independent if it was perfectly identical. If it was perfectly identical, then it completely...
It doesn't matter.
Now you have the same probabilities. Does that make sense? So now this looks perfectly independent. Like it looks like we can't say they are independent for certain, but now it looks super duper independent. So think about this. This was the most likely thing to see given the null. So what do you think the p-value is? Now I want you to hear the language. This is the most likely thing to see given the null. So what do you think the p-value is? Just listen to the way it's worded. This is the most likely thing to see. Most likely. So what do you think the p-value is? High. And how high? Most likely. So what would the p-value be? Which goes to theory of p-values. If it's the most likely and the p-value is high and this is the most likely, the p-value has to logically be what? Well, it's going to be about 0.05 definitely. And if this is the most likely thing to see if they're independent, which would be no difference at all, the highest possible p-value is what? The highest possible p-value is 1. If this is the most likely, it means the p-value is as high as it goes. Priya got it right there. It's p-value of 1. Great job right there, Priya. That's it. It's a p-value of 1 because it's the most... This is like... We're saying the p-value tells us the likelihood of what we saw by random chance given the null is true. So if the null is true, this is the most likely thing to see. Now tell me, we now see some differences, but these differences here look rather small, right? So if these differences are small, they could be likely by random chance. Does everyone follow me here? That the differences you're seeing here, I'm going to try to make it so you can see it all at one time. The differences you're seeing here are small and likely by random chance. So the differences you're seeing here between the mosaic plot are small and likely by random chance. Now notice as the differences get bigger, what happens to the p-value as the differences get bigger? Do you see the differences getting bigger here? As the differences get bigger, the differences are what by random chance? As the differences get bigger between these, the differences become what by random chance here? So as the difference got bigger, they became what by random chance? To see it once again in action, here's no difference, and now the difference is getting bigger right here. Look at the graphic to see the difference getting bigger. As the difference gets bigger, they become less likely by random chance. The p-value decreases because the p-value tells us the probability of seeing these differences given the null is true. So think about that. When we see small differences here, it's possible the null is true. It's possible that attending the review is not really associated with your grade, that they're completely independent. But as the differences get bigger, we reach a point where the differences are unlikely by random chance. You might say to me, well, with Brian, only of the people who attended the review, only 35% made an A, and over here, only 29%. That's a difference of only 6%, Brian. You're telling me that this 6% difference is significant? Well, yeah, because these differences between the people here who attended a review yes and attended a review no and made an A are unlikely by random chance. Where the smaller difference, will it actually update those? No, I've never done that with the things on there. Oh, it will. That's so cool. And it's almost to where you can see it really well. There we go. Now the differences here, which is 2%, are likely by random chance. Great job, John, right there. You're welcome. And that's the concepts. That's what the p-value is telling us, that this difference of 2% right here, 2.22%, that's neat, repeating decimals, is very likely by random chance, or likely enough that we would not reject the null hypothesis. But that's got it. Any last questions? Now the difference here is going to be ridiculous. Now it's basically impossible by random chance. And you might say, well, it's only 15% more. And you'd say, well, according to the way the math works out, this is a very, very unlikely difference by random chance, given there is no difference between these. They are independent of each other. We have reason to believe that attending the review is associated with the grade you make. So I reject the null hypothesis that attending the review is independent of your grade at a p-value of basically 0 at the alpha level of 0.05 with a p-value of basically 0 at an alpha level of 0.05. I have evidence from my alternative that attending the review is associated with your grade in the class. And here's one big thing to know. Oh, where's my sound on that? Oh, did I mute that screen? Last thing to know. Last random thing to know. Oh, wait 2 seconds. You're about to hear it. Headphone warning. Okay. You're welcome, Kendall. Last thing to know. Can we say attending the review causes you to do well in the class? Can we say attending the review causes you to do well? Can we say that yes or no? Can we say attending the review causes you to do well? No. We do not show cause and effect unless we do things like experiments. We do not say words like prove or accept. Oh, Crabrave? Curio, I'm sorry about that right there. Thank you for the Crabrave in the chat. Curio, we undid that right there. Keep showing up, Curio. If you show up a whole bunch, have some questions, we'll mod you. We sometimes mod random people who are. So I appreciate that. Don't listen to Mubot. Mubot, stop being mean to people. We can't say it causes, or we can't say it proves. We don't say words like that, especially we don't say prove in stats. We say we have evidence, or we did not have evidence. Curio said it perfectly, that we failed to find evidence, or we didn't have enough evidence to reject the null hypothesis. And we'll head back here to the main screen and say bye for now. I want to say excellent job right here, everyone. We've been doing lots of review. You're welcome. We're going to do we'll do like a little bit like an hour review tomorrow. And then we'll do the Kahoot. Curio, you're welcome to join our Kahoot. Look for the Exam 3 Review Extravaganza. So if you join in, win the Kahoot, we'll probably throw more prizes. I give them out to UT students. So only if you're a UT student can you win the prizes. But Curio, you're welcome to join in our Kahoot and have some fun. We always like when people come in, join in, and have stats questions. So grab some food. Oh, that's awesome. Are you taking stats at another university? What do you do, Curio? What are you doing stats-wise? Doing introduction stats? What stats class? I'm glad the VODs have helped you. Videos on demand's right there. If you always have questions, feel free to jump in and ask. We'll hang out for a half second more. I'm gonna get a crawfish boil. That sounds awesome. Could do a crawfish boil. You're welcome, Kristen. It's practice, practice, practice. Studying data science, that's awesome. Are you using R to do your work? If you're using R, do you do programming language? I'm assuming with data science. That's what we do here, and you don't have to say anything about where you're at or anything like that. Don't worry, like that's as long as you feel comfortable with saying what you're saying online. So yeah, that's like studying stats, doing intro to stats, doing data science. Well, I'm glad this has helped you out for probably where you're doing it at your university. Love R and Python. Which do you pick? Which do you pick? Do you pick R or Python? Curio, I'm going out on a limb here. I'm just gonna make you. I'm going out on limbs. I'm going out on limbs. Making Curio a mod right here. Going out on a limb. You know your data science sounds like to me. Leo is saying Python. I'm neutral. There is no neutrality on the war of R and Python. I'm a fan of R, but Python's quite excellent. Both are great. Both are great. Like they are. R is more like statistics, where Python is more like more true programming. I would say not like R is not true programming, but I see a lot more like programmers using Python. I see a lot more data science using R. So I think you might have that right mix. And so does the mod title carry even after it does, Kristen? You hang on to mods. I haven't. The only reason I would demod people is if not wrong music. We're doing chill music. The only reason I would ever demod people is if someone was like, like I don't know, like blocking people or something like that. So I haven't had to demod people. But yeah, it's the only reason I'd ever do it. Yeah. You're welcome, Leo. So Curio, swing by anytime. You're always welcome here to chat and ask questions. Especially I mod sometimes people because sometimes my students, especially on a stream, might like be like, who? I don't know. But yeah, Curio, great job. We appreciate you being here, asking questions and practicing reviewing. Well, until then, everybody, we'll be back here tomorrow. Swing by, ask those questions. Yeah, swing by, play the Kahoot. Maybe you'll win. You'll be like, I won a Kahoot at another university. If so, or you might be at UT. I don't know, maybe you're doing data science at UT. Never know. Anyways, we'll see everyone later. Bye for now. Bye. Thank you, Kyle. Keep up the great work, Kyle.